working. Change it. Change it when the speaker.
Everybody take notes? Yeah, all at the same time.
You are currently the only person in this conference.
Sweet. I think I'm not speaker anymore. Do I just take speaker? Yeah, I'll just click the button. Yeah. Slides change. Okay. Okay, it's 9:30, so we're gonna do the conference stuff. Hey, everybody. Yeah, thank you. Okay, conference time. So, intro slides. I think I managed to screw them up slightly this year, so I just have this one slide. So, this is Plumbers. Most people have been to Plumbers before. If you haven't been to Plumbers before, very discussion-oriented conference, so you're expected to talk to folks and whatnot, not have a ton of slides and give a presentation, have actual discussions and such. So we'll try to enforce that. There's a toss around microphone in the back. And aside from that, just try not to give a talk. Or try not to be caught giving a talk, I guess maybe the way I say it. You have to give a talk. But anyway, we thank the sponsors. Without sponsors, we wouldn't be here or get food and such. So always good. Aside from that, we have a code of conduct. It's not on the slide this year, so just don't harass people. I kind of never had to read it, so generally don't have problems. Should be pretty straightforward. Okay, I think that's it. I don't know if folks have questions. Note taking. We're supposed to take notes. There's a shared notes thing in Matrix, BBB, whatnot. So please use that. Sometimes it blows up, and if it does, I was told to just put things in a text file and then paste it in. So yeah, that's always how I take notes. So I've never figured out the computers. Yeah. So, but at least I'll have a couple people take notes. There's usually a couple people who manage to do so. Those are good for later and hallway tracks and whatnot. So cool. I think that is it on the intro side of things. Unless folks have questions. or there's something else on these other slides. I think these are the slides from before the conference. Yeah. Cool. So we'll try to stick to time. We got a couple of minutes because there's a bunch of remote people. So next talk starts in 3 minutes. What? You want me to just start? We usually don't start early because of the internet people. Oh, I'm late? All right, well, here we go. I thought we were 3 minutes early. I thought it said it started at 05. Okay. Sweet. Here we go. Okay, so I mean, I guess we can just get going, or we'll just get going. I don't know. Waiting for 3 minutes at the start seems kind of silly. Here's my deprecating stuff talk. I have one slide. So I kind of scanned through the kernel for a little bit and came up with some things that I thought might be interesting to deprecate. We've never deprecated anything before, as far as I know, so we don't have any sort of rules. So I don't really know what people might want to deprecate. But in my mind, it's stuff that is unlikely to have any sort of real users anymore, right? So some of this stuff is just kind of old and has stuck around because we have it. So I think in that category, stuff like XIP, likely nobody uses that. I've never managed to use it, and it does not build def configs and whatnot. Yeah, because we don't have enough space. It certainly doesn't build all yes configs, and you have to do some fairly specialized things in order to make it work. So never managed to make that work, and it's a bit of a maintenance headache. You know, like it's not a big one, and none of these are really big headaches, but when you add up a bunch of small problems, you kind of just end up slowing everything down. XIP is one of those things where folks don't test it, so I do some build tests and whatnot, but I occasionally end up kicking back patches fairly late in the process in order to basically add some XIP macros or whatever because something doesn't build, and it's not clear that anybody is actually booting any of these kernels. Yeah, so I don't know if folks have opinions on this or any other specific ones. That's kind of been my mindset for what this deprecation list is. Now, RV32 was on the list, but I think a chip showed up. Yeah. Right? I don't know. Yeah, I think the Andes guys have 32-bit IP that is in some chip that got announced like a couple of weeks ago. Right? Yeah. So I think that means we're stuck with it. I mean, if there's a chip, people are using it. Right? I don't really, this is the things like, I don't really know what the rules are on does anybody use it, because it's been kind of unused for ages, right? We have compat mode now. The main driver for the 32-bit port was really so we could run the GCC test suite on QEMU. That was kind of the primary user. We didn't have any silicon. With compat, that 32-bit user mode side of things has kind of disappeared.
Just deprecate if someone complains.
That's, you know, and that's kind of the other half of this is how do we actually do the deprecation, right? So I was thinking that's basically, that's kind of my theory, right? Let's maybe like toss in a config or something. So anybody who was building these now is broken and has to at least update their kconfig to say deprecated, right? Because, you know, not everybody just reads the mailing lists. Maybe in this case, if you're not on the mailing list, it doesn't matter. Right? But if we at least put in some sort of active, because most of the stuff is hidden behind config non-portable now. So if we put some config, we're going to delete your stuff next year type thing, then at least people have to look at it. And maybe we add some on boot warning or whatever that says you're in some deprecated config, tell somebody lest we delete your stuff, you know, January 1st, 2025 or whatever dates we pick, right? Anyway, so yeah, I don't really have the entire 15 or 20 minutes or whatever to fill here. So if you guys have, yeah.
So like the individual RV32, you know you might not be on the level, but the combination of those two can be 97, and then you know, so some RV32 microcontrollers can actually run or microcontroller class processors that are actually powerful enough to use I've done it. I
Yeah.
But, you know, most of it as a provide and not necessarily as a, is that actually something I.
And that's kind of where I see everybody in no MMU mode right now is like, it's a demonstration to say we can do it, but nobody really has a whole lot to do with it. We did not even have an FTPIC ABI. You want the mic? Can we grab the, yeah. So we did not even have an FTPIC ABI. We may still not have an FTPIC ABI, but there are at least patches for FTPIC now that I forget if I merged because nobody knew who was supposed to own FTPIC, right? Yeah.
The thing about LMU is pretty much everybody is just they are because we have 17. Pretty much everybody has stopped using LMU in production across all the architectures we have. I think Taiwan does still do LMU. Extensor is the only one that's actually being worked on, I think.
Okay.
And on ARM, we have the largest user base traditionally, but I think all the ones I've seen for the past 6 years have been people doing it.
Okay.
Not pushing products.
So that seems like a straightforward one to propose deprecating.
We have, to some extent, we have no new and started to support K210 that I assume people were still using that to, I know people were using it at some point.
Was anybody using it to do any?
So I don't care if it's not C+7 or whatever previous kernel. So I'm not going to map that. I mean, if you want to deprecate, go ahead.
Yeah. And also we never,
It's not being sold anymore. So.
yeah, there's a two. Sorry? Right. Damien says he's not going to knack it.
No, go ahead.
And like you said, the K210 is defunct. There's a 230 now. I haven't actually done anything with it, but it's on my desk.
Yeah, they have like a cover in it.
Yeah. So also K210, like 8 megs of SRAM.
That was the point. That was the challenge.
And that is the hardest part of doing anything on it, including like, you know, user space. So not convinced anybody's really done a whole lot with it. Right. But you know, we're not gonna like make decisions, right? We gotta go do mailing list stuff and whatnot because not everybody's here. But that's kind of my general thought process for how to decide what to deprecate is if there's something in there and it's unlikely anybody's really capable of using it anymore, we should get rid of it, especially if it costs something to maintain, right? I think SBI 0.1 also likely a good one to toss, except Atish has disappeared. Atish was saying it's the only SBI debug console way we have still.
I think debug patches are on.
Okay.
Because there's some use case where people want to get the
Yeah.
So on that mode, I think we can remove the 0.
Yeah, like I still test 0.1 sometimes because it's the only reliable super early debug console.
Yeah.
But that's only when something else is broken. So yeah, anyway, so I think hopefully we can toss 0.1 after that, and presumably the spin weight boot stuff as well, which kind of never worked that well anyway.
Yeah, I don't know anybody actually uses 0.1 for spin weight boot. Only the legitimate use case was the debug.
Yeah, I think since we moved everybody over to OpenSBI from BBL, we're not stuck on spin weight boots anymore. Okay, so.
If somebody has some other firmware that still relies on the spin weight boot and don't use it.
We'll deprecate it and then they'll tell us. Right? Like I don't really know what else to do there. Especially if it's some of these like embedded ancient kernel type stuff, we're not going to find out for like 5 years after we deprecate something. So. For ages, yeah. And also it disables a bunch of other features that we like. So I think that's likely an easy one that no one's using. Medlo, we have talked about deprecating Medlo a couple of times because it breaks something that I've forgotten about. Breaks the build all the time because you have to remember to do the fake pick that we do for medini for a couple of random files. But there was some feature we were trying to merge like 6 months ago or something where we said, hey, let's deprecate Medlo, and we post about it and all that sort of stuff, and nobody said anything. Do you remember? It was your patch. Do you remember what it was? Yeah. Okay. Alex doesn't remember what it was either. I think it was Alex's patch that was incompatible with medlow for some reason, some memory refactoring thing. Anyway, doesn't really matter. But we at least did discuss deprecating that, and basically nobody said anything, and then that was kind of the end of it. So probably we can throw that in the list too. Maybe that's the first candidate to actually deprecate because we talked about it before. Non-relocatable kernels. So when those went in, the theory was that basically everybody's going to use the relocatable kernels. They were slightly more expensive at the time, right? But I think now that we have all the multilinear map stuff, they're not even more expensive anymore because we're doing all the same stuff to first order. So just get rid of those, right? Unless somebody really cares about the small cost. Medlow is in a similar spot. There's like a small additional cost where you can save some global accessors, but it doesn't work for relocatable kernels anyway. I think SMP equals N. I think a bunch of other folks went always SMP. Yeah,
P1 what is the single core? And we agree about that.
Test that scenario for one of other cases. So like early bring up, so you kind of you want to do it, and people.
yeah, that's why we have the config option.
So this is the one that certainly has a cost.
Yeah.
Writing all that from P for stuff.
Yeah.
On the other hand, like on RV64, we never supported on SMP kernels, and we're fine on a single core.
That's kind of my rationale, right? So though I buy the argument that we have some very slow single processor systems, also have buggy memory systems, and might get a little confused by any sort of complicated stuff that we do in SMP land. That would kind of be my worry there, is if it really falls off some cliff, like on the D1 or something, right? Yeah.
I mean,
Yeah, but do we care about a couple of % performance on those chips? I don't know. You say yes? I don't know. Like, I genuinely don't know, right? Like, and SMP equals N for us is not really much of a maintenance burden, right? Maybe every once in a while something trips up as a build or something like that, but it's easy to test. So yeah, some stuff turns into no ops, right? Some fences. It's all mostly generic stuff, but some of that hooks into RISC-V. Sorry, I forgot to repeat it. Damien is asking what actually is the difference. Almost all generic stuff. That's why it's not that hard to hook into. Yeah, you want to throw it back to Sam? Yeah. Yeah, there's loads of little things, like all the memory barriers basically go away, or large chunks of them basically go away, right? So there's loads of things that get a little bit faster. Yep. But the question is, does anybody care? So maybe the answer to that one is yes. Enough people to here do. So, and it helps, like Atish said, with pre-silicon, which is kind of nice. I don't know if we're allowed to say that, but it does. Yeah. Yeah, it's okay. So we'll just keep it then. It doesn't cost me anything. So it's in my, all of these are in my.
No, I mean, like some patches in the build lots being run out on it.
Yeah, I don't know. You mean like LKP 0-day stuff? I don't actually know what's in that list of configs, dude. Yeah. Yeah, there are people who test these things. That's part of the reason they're on the list, because they do occasionally kick back patches, right? If they weren't kicking back any patches, I guess I wouldn't even remember them. Yeah, I agree. And it's almost all generic code, so I'm okay keeping it, right? All these things are just on the list because they're things I don't use and I don't see a whole lot of people using, if that makes sense, right? But yeah, we'll just keep it like.
Let's start the focus with the ones that.
Well, none of these really cause me pain. Well, the thing is that none of them really cause me pain because I don't test, I don't boot test the things that I don't care about. I do build test them, but that's really pain for other people, because when you send your patches and it takes a while for me to get back to you saying they don't build, it doesn't bother me. Like, I build test the code I want in. It's not my problem. And that's really my worry, is that it's causing pain for other people who don't test this stuff and think, oh, why do I need to deal with XIP macros that probably don't boot anyway? You know?
But I think a lot of things are just kernels that care about memory size a lot.
Yes.
And they also have very customized kernels that probably have a lot of capital.
And maybe that, especially something like XIP, maybe that's it. And maybe people are using the core code and they've just fixed their bugs and they haven't upstreamed them, or they don't run into them because they're not doing all these crazy generic things that we find. So
If you are less than 30 then
you don't have to. We have 8 megs of RAM with no XIP, but you can't really do anything. Yeah. Unfortunately, XIP requires MMU, so it's kind of a weird small system problem, if that makes sense. Yeah.
MMU doesn't like small memory.
Yes.
Most of the MMU uses small memory.
Yeah. 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 I think if you had DRAM, you could probably also afford page tables. We have the FTP patches. Yeah. Yeah. Good. Now we have users. At least we have user space. Yeah.
So there's actually 3 things. The kernel is in Flash, or is this having executable Flash while being able to write to it, or is this about having user space pages?
I believe this is only executable kernel pages. Does somebody know for sure? I haven't looked in so long, I don't even remember. Kernel text only. Yeah. But I forget if you provide like like very simple init-rd that doesn't need to be unpacked, or isn't there some way to do that for, is that not true? Yeah. So I forget if that works or not.
We actually did some work on ARM 32-bit work again, but it was probably ARM64, it's never worked.
Yeah, and sorry, worked is a vague term here. I forget if there is any code in the kernel to enable that. Certainly it's not something I test. So it's unlikely it does actually work upstream. Yeah, and that's part of the reason it's hard to test, because I don't have all that stuff, basically, right? Now we could test it in IOMMU if we put some time in, I'm sure, but I've never managed to get a system working. Connor says he doesn't know if it works. Yes, I agree. And that's part of the reason I think it doesn't work, is because we've been through enough rounds of things where I'm like, gee, somebody really needs to test this on XIP, and nobody has. We probably broke something at some point. Like, it's unlikely we made no bugs for like 2 years or whatever it's been. So, yeah. Yeah, it just touches a lot of little things, but it's, you know, it can be done. And fixing it is probably as much work as just resurrecting it. So, right? Yeah. Cool. So I think the only thing other on my list were the old tool chains. So the I 2.2 was when we moved a bunch of instructions out of the base ISAs and into not custom, this is small standard extensions. And we have like a page or two full of kconfig to try to detect the various forms of toolchain weirdness that resulted in. And I don't know if anybody wants, it's like GCC 11 or something. I don't know if anyone's still using that. Yeah, it works, I think. People test it sometimes, which is how we find the bugs. So I don't know if we just have actually found all the bugs, or if everyone's just kind of moved off of the old toolchains and have stopped bothering to find them. Right. That's the thing, is it's not that old. And a lot of like our, vendor type people just don't update these things. So 11's only 2 years old. Do we tell people? But also 11 doesn't have working like, C++ atomics. So yeah. But are they also updating to the latest kernels? Yeah, I don't know.
That could be something that's just worth its mark to deprecating, even though now it's just this seems like something that is going to need.
Yeah. Yeah. So the statement was, this eventually we're gonna have to deprecate old tool chains. So let's mark it deprecated now, not put a date on it, and just kind of see what happens. Yeah, and we've kind of never really sat down and deprecated any of our old toolchain and binutils versions in RISC-V land, even though some of them are close to 10 years old now and definitely had horrible bugs that people should not be using. So maybe we should scrub through it and say, well, if people are using it, we'll still keep it building and whatnot, but you really shouldn't be using stuff that old because it's probably super broken.
Besides time of it being old, what was right?
Well, for example, like the C++ atomic bugs that we've only fixed in 12 and 13, you really shouldn't be building user space with 11 because you'll get atomics that don't meet the memory model. It is completely independent, but how else do we tell people to move, right? Yeah. Yeah. But if they have the old binaries, there's nothing we can do about it. They're broken, and hopefully nobody's manifesting bugs. Yeah, Damien says distro people, and that's kind of my theory, is that if we say something somewhere, don't use it, that's enough to get people to look at it. Or maybe it's not, who cares? Yeah.
Usually, I don't think we've ever deprecated toolchain without completely. Usually what we do with the kernel is to try and say this is all. The broken of the old version is that very few people use it, so we just make it necessary now.
Okay.
So overall in the kernel, we still support 5 and the next level probably 68.
Okay, so maybe we just don't do anything in RISC-V land and wait for everything to tick around in another 5 years, whatever it is.
Have a higher requirement for one architecture.
Yeah.
And that wouldn't make it deprecated first. I would just, if the time has come, we just say, well,
Okay, yeah. And that's, we basically started out with some higher versions because like I forget what we got in first was 4 or 5 or 6 or something for GCC, and it was like super broken. So we basically told people don't use that, all in a couple of places in the stack. But I don't think we've done anything since then. That might have been just glibc or something. So
maybe the first step on that would be to find out what the oldest sensible toolchain is that still is the prior to 11, and you can then make it 9, you know, that or maybe later.
Yeah. But we should at least, even if it's not for this I 2.2 stuff, we should at least go figure out what tool chains we support. That would probably be a good thing to tell people, right? So, okay. I only have 1 minute, I think. So, yeah.
The other kind of problem with it is, I think the proper I 2.2 support for communicated like 17.
Yeah. So I think we're stuck with at least half of the hacks.
Yeah, because most of the hacks are not about, okay, your particular toolchain. It's mixing this and this.
Which is where the pain comes in, right? But at least if we say we get rid of like old BFD LD versions, we only have to deal with the LLD problems. So there's some amount of benefit to be had there. But you're right that like most of these are people mixing stuff up. So we don't really, I mean, there's no way we can deprecate Clang 17. That's the current release, right? Yeah. So that's totally, we can't just say don't use Clang anymore. That's totally unmanageable. Okay, cool. So I think, yeah, I'm done. You're next. Okay, cool. I should probably do
Hi, hello everyone. I'm Gordon on the slide.
Clicker should change the slides.
Okay.
Just click on presenter.
Okay. Hello everyone. I'm Gordon and I'm from Alibaba RISC-V ecosystem team. And today I would give a talk about the RV64 ILP32 ABI. Yeah, that means to run the ILP32 data type software on a RISC-V 64-bit ISA hardware. Yeah, it's an old topic, but new to the RISC-V. Let's have a quick recap on these popular ABIs. Traditionally, we have the 32-bit ABI. Actually, that means RV62 ILP32. And we have the traditional 64 ABIs, such as RV64 LP64 ABI. And then this topic is, and the last is today's subject of the 64 ILP32. And the difference between them is the 64 ILP32 with the 32 LP32, the difference is only the ISA difference, but they have the same data type. And the difference between the 64 LP64, the only difference is the data type. They have the same ISA. So 64 LP32 is standard these two ABIs middle. Yeah, so it's combination one. And here is our work. We have. Okay, we have two. I know one I raise up why that's the motivation discussion. So our agenda is we have two part, the motivation discussion and the implementation discussion, and I would answer you in that discussion.
Understand implementation and going through all the
Okay, so.
it would be having more context would be nice.
Okay, let's direct. Let's skip that slide. I mean, okay, I just show you how the work is. Yeah, what we have done. Yeah, that's it. We have completed the user space and the kernel space, the 65 ILP. I think all people here in the room know what's happening. Yeah, so we skip that and directly move to the why. Yeah, why? Okay, motivation. Why? Okay, so there have been a lot of 64 IP APIs such as x86, x32, and MIPS N32 and ARM64 ILP32 all existed, but none of them succeed because not widely used. Most of the usage maybe just for the extreme benchmarking. Yeah, we have talked about this many years ago, 10, 20 years, maybe. Okay, it's long history, but it's just like magic event. It's turned to the RISC-V. Yeah, that's I need to explain why we need to do that. Because there are a lot of time memory device come out with the RV64 ISA. This chip is very hot in, they are delivered and shipped very widely. And they have a lot of people use that, such as the Milk Fido and D1S and the OX64. You can find that in the YouTube. It's very hot. A lot of people use that. And they all have only 64 megabytes memory, okay? So this vendor asked me, how can I run ILP32 on that? So that's my, so I know you question why these people need ILP32.
I get the idea about the software. Why create such weird?
Okay.
Why make it a 64-bit SoC? Because 32 would be fine if you don't
Okay.
have that much memory.
So
One way they can run ILP32 is to run our.
Actually,
okay. So I know I'm the okay. So, go ahead.
There's no software system for everything. I'm quite done with finishing. All the legacy 32 guys can just use,
Oh.
if you want. They're quite small.
getting the replacing one column with another is not solving it.
Because there is properly no ILP32 on RV64 software.
Okay.
Yeah, and that's going to be a horrible one.
Rules.
Okay. Can I continue? Okay. So I will explain. So you have so also so when I introduced our processor, because we only produced the 64-bit ISA processors, we didn't produce 32-bit ISAs. So when we ask my customers why they need ILP32, so I also needed to figure out what's the reason of that. So I try to do that. I make some measurements, try to explain your question. Yeah. Firstly, we tried a tiny configure of the Linux kernel, a tiny configure with just 16 megabytes. This is a use case, and we found that the RV64 ILP32 cost more than 25% of the memory footprint cost than the RV64 LP64. Yeah, we use the tiny configure, and we also remove some 64 special configure to make them. You could look at the bootloader. They are line to line equal, so they have the. We just want to make the similar. When you compare the 64-bit and the 32-bit. So when you compare kernel into the ILP32, you will got better memory footprint. So that's one reason I found. And the second is for the extreme benchmarking. I mean, if you have the ILP32, you have better data density, you have a better cache utilization, and you have a small data workload, such as the 429, this benchmark, the input data is cut down into 8 megabytes. If you use the LP64, this input data is the 1.7 gigabytes. So ILP32 is smaller and increase the data density. Yeah, and this picture show you how the improvement is. There is the positive improvement, and and I also get some negative improvement. Yeah, you go ahead.
This is the super spreader mic, right? That's how it works. So, I spent 10 years on the various different ILP32 like ABIs, right? X32, ILP32 on ARM. Every time spec came up, we basically laughed and said, if you see an ILP32 spec benchmark, you're going to ignore it. The only people who don't ignore a spec benchmark with ILP32 are those people who don't know. But any customer who knows is not going to take an ILP32 benchmark because they're going to say, that's not the real ABI that I'm using, right?
I think the situation in the RISC-V is different because RISC-V don't have the existed traditional 32-bit ISA ecosystem. That's the problem. And in ARM, in the x86, you have a very strong and robust 32-bit ecosystem. So it's hard for people to change from to build another new 32-bit ABI because this takes a lot of hard work. But for the RISC-V, there is no existing hardware. So our 32-bit ecosystem are just a startup. And who is the standard ABI? 64 ILP32 or 32 ILP32. So it's very different from the x86 and okay, you can have.
All good point, but my answer is trying to solve all that 32-bit ecosystem problems by breaking the fundamental stuff that we got used to with 64-bit architecture is just a bad idea. I mean, going forward is going to be a nightmare.
And this also just makes it more complicated because we go from having two 32-bit ABI, sorry, one 32-bit ABI, two 32-bit ABIs. Like you're not fixing the lack of software problem. We have to start everything over again. Yeah, sorry, I lose first.
I just wanted to build a point that like on x86, they had to support this because it's a legacy thing. They always push up in the 16-bit mode, and then someone takes it to the 32-bit.
Yeah,
this is x32. The fact that you have a kernel bit says something.
Yeah.
But
the Intel X32, like the x86 X32 mode, is only for spec CPU because you get better results in spec CPU. With X32 mode, then the neither 64-bit or 32-bit later binary.
And it's MCF, which is dead anyway. So
yes,
who cares?
and it's also the only reason why people try to push it in ARM, and the took us a long time to write that, but we did not merge it with the kernel. We are very lucky that we did not do this.
Okay.
The benchmark people still want it.
Okay, so I used to work for Android. I wrote the last one side. I know why Intel was telling us to use X32. And the reason it's got nothing to do with extra registers and things like that. It's PC relative addressing. Android by default has ASLR, happening in code. And X8632 lacks a PC relative base, so it's still being X everywhere. The estimate's like about 10% performance loss because of the actually losing the register. So X32's reason for existing with Android is that the system can use land until Apple changed that. And the reason the X32 happened was because of PC loss and not virtual registers. But I like your concerns about memory footprint. In medical enzymes, you have compressed pointers and things like that. Maybe this is not even for compressed pointers in the kernel.
I think for the memory footprint, if you use the IOP32, it's significantly improved. Yeah, and for just the 64, look here, our products also with the very tiny memory, and if you use the IOP32, you will get the advanced. Okay. So here is we try to convince our customers to change from the ARM32 to the RV64 because they constantly use the IOP32 before, and we tell them that IOP32 could run on the RISC-V 64 properly. So they okay, if you use the IOP32 could run properly, then they would try to move to the RV64 because for the memory footprint, mostly for the memory footprint. And we also told them if they change it from 32-bit ISA to the 64-bit ISA in the Linux kernel, you will get a lot of benefit from the other side, such as 64-bit ISA could improve the memory copy, perform the memory operations, and here is the comparison between the traditional load word and double word, and they are significantly improvement. And the second is ePPFG. If you use the 64-bit ISA, you would have the proper ePPFG implementation, yeah, and that would be faster, yeah. And another thing is the 64 IOP32 have a better atomic 64. And from our practice, we found that RV64 IOP32 could share with LP60, could share with the traditional 64-bit implementation a lot of code. We can share the code, we can share the ePPF implementation, we can share a lot of stuff. So just implement. When we talk about RV32-bit, we should need to separate them. One is the RV32-bit ISA, and one is the IOP32 data type. Actually, I also agree that RV32-bit ISA should go away, but the IOP32 data type, there is a software scenarios. Still, a lot of people need a 32-bit software usage. So that's my opinion.
There's already no software system for either of these right now. But using IOP32 and RV64 gives you more flexibility because you do get the double wide registers, you do get double wide atomics, and you do get double wide stuff in the kernel, as opposed to RV32 where you get none of that.
I think the biggest point about him is that you can run it on the hardware, which does not have any native LPC32.
We don't produce any 62 ISA hardware, and that's why we do this job. And we have finished the Fedora RV32 because we implement the compact mode. But for the kernel side, for the M mode and S mode, we still keep the 64-bit ISA. And we have finished the Fedora. Fedora could run properly with the 64 IOP32 kernel side, and the compact mode with the user space. And now we are working with the total 64 IOP32 ecosystem. And this year's goal, we want to deliver Fedora 64 ILP32 distribution first. Maybe this is the first total 64 ILP32 distribution in Linux.
The other possibility is
Okay.
run either ILP32 or LPC64 on the same hardware. You don't have to RV32 hardware.
We have UXL now, though.
Yeah. You started with the point that this is for hardware is tiny. You don't run Fedora on hardware that long.
Actually, this hardware, what I mentioned is tiny hardware, right, correct. But yes, I didn't find scenarios in some high performance hardware. Maybe some high performance hardware, maybe just for the extreme benchmarking. Yeah, maybe for that. But most our requirement is from what we look from is from tiny memory hardware. But don't look down at this kind of companies. They are massive companies, and they will grow up. Next year, maybe they will produce some.
Size of types that new have registered on the 64-bit architecture. I just think that's fine. That's all. If everybody wants to do it and put in the kernel, I'm not going to say anything. I just give my opinion. It's fine. Christoph will not be happy with it.
Just talking about a lot of different things here. I think running ILP32 user space on 64-bit hardware in general is a very sensible thing. You do it on ARM all the time. It is very useful for having small memory systems. If you can run the normal 32-bit user space with the existing toolchain support, that's there with GDC, whatever, go ahead and do it on the 64-bit kernel or on the 32-bit kernel, doesn't matter. 64-bit kernel supports it. Do the same thing on all the other architectures. Do the next thing to do it on ARM. Do the RPC. That just works. Okay, but not more.
Okay.
Well, there's 1 minute left.
Okay.
But a new ABI is a huge maintenance cost for the toolchain for user space. Don't use that. Like user space, having a third ABI is a cost that nobody should pay for this. And we try very hard to avoid it on ARM. And it was a mistake on NIPS, it was a mistake on x86. We should never have done it.
Yeah, we have a team work for it, so don't worry about it. We are working on this. Okay. So I finished. So that's what we are doing. We are let the 32-bit. Yeah. Okay. Next.
The auto switch. Yeah, that's me. All right, I guess this one will be much less controversial. So relax and breathe and everything like that. So we're talking about CI, which everybody loves. I'm Bjorn, and I used to do networking and BPF. I still do, but here at RISC-V, I ended up doing CI. So I'm the CI guy now. Cool. How do I switch like that? Okay, so a little bit about the rationale for the Patchwork CI. So it's pre-merge hook. We try to do build things and sort of get a notion: is this good enough to merge? And get off Palmer's back pretty much. Yeah, I'll run through how it works, and then we can talk about the things afterwards. What else? Short history. All Patchwork or all subsystems have their own Patchwork CIs, pretty much. We as well as the RISC-V. So we ported. We started out by running the NetDev ones called NIPA and ported that to RISC-V. So it's running on Connor's. Where's Connor? Connor left. He didn't want to be around.
Yeah, someone's name on the top.
Okay, cool. Anyway, so Kernel has been hosting the old Patchwork CI for quite some while, and it's been running on the on a microchip machine. Anyway, so it was time to move on. So a lot of problems, not a lot of problems. It was working, but you know, that guy that comes in, you're back, Connor, welcome. Ended up doing all the work. So if the CI broke, which is, you know, as with all CI, yeah. Right. Exactly. So it ended up being all the work for Kano. So we figured let's try to change that. So there's then this RISC thing came up, which you can think of like Linaro, but for RISC-V. And we got a bunch of VMs. So we figured out, let's move to GitHub. It's not like we love GitHub, but it's it's what most people use, and it's sort of, hopefully we can get some, you know, community thing going on. We'll see. So instead of using the pile of Python that we're using at Microchip, we moved to something. What's that? Yeah, right. We moved to something that Meta was using for BPF. So my background comes from BPF, so you know, pick that up. So Meta was they published their KPD source, which is the kernel patches daemon, and the grand plan is like this. So hopefully it'll be something that'll easier to maintain. If we're lucky, we get, you know, contributions from the community on the CI. It's not like that'll happen. We'll see. And hopefully easier to scale. That means we can just add GitHub runners if we want to, you know, speed up the build. And all of this is hosted on GitHub on a project or organization, whatever you call it, on GitHub under the Linux RISC-V. Cool. So I'll just, you know, blast through how it works. So the thing in gray is running on the Google Cloud. So the kernel patches daemon starts out by syncing all the Git trees from, you know, what do we have in RISC-V? We have the for next and we have fixes, and now we have also a repo with the CI source. So it starts syncing the Git repos. It'll pull in all pull in a series from Patchwork. It then takes it bakes the Git tree with the CI files on top of it, and then the new series. So if the series fails to merge, then that's the first thing. So it doesn't merge and get it doesn't work. If it managed to merge it, the build will be done on one of the dedicated GitHub runners. Build completes. We have some results, and then the daemon will scrape these results from the pull requests and publish it to Patchwork. And you probably have seen all these traffic lights, right? Quick about that. It's the patches daemon, yeah, again from Meta, and it's go ahead. Wait for Mike. What's that?
The previous slide, the last box, the one I'm seeing that correctly.
Yeah, it is.
Table tree we were talking about.
What's that?
Greg's table tree, the GH RISC-V. What's that?
Oh, the bottom one.
Yeah.
Yeah, that's right. That's a GitHub pull request.
Okay,
Yeah.
that's GitHub.
Yeah, exactly. Good point. Yeah. Cool. Okay, that's a daemon that scrapes everything. I won't go into those details. What else? Maybe this is a bit interesting. So what we do is that we have this GitHub CI, which is called workflow in GitHub speak. And we just directly ported what we did with the old CI and pulled it to GitHub. So it pretty much is a pile of bash, and we glue it together with the YAML. So that is while it's possible to run a GitHub CI locally, it's easier to just have, you know, a simple local bash file that just type make and it's solo or build or whatever, and it'll mimic what's being done on the GitHub runner. If that makes sense. Cool. So here are the tests. So right now, this is the only things we're doing. It's we build 32-bit, and so also I'll get back to this ties into like what Palmer and Ren was talking about. Like, how do we sort of try to keep the build matrices sane, which is we'll get into later. Yeah, we build 32-bit, 64 bits for various flavors. You know, muscle without muscle, stuff like that. A bunch of checks. Pretty much. Right. So for the runners, we're using a Docker-based build, and we're doing cross-compilation on the RV64 system. We're using the tool chains from kernel.org. There's some other tools, and we're using something that in Git has been called ephemeral runners, and that's pretty much just saying that, okay, when you enter a build, you have a clean state, which for some reason is not the default for GitHub. So usually you have just when you enter the build, you have like, you know, like a dirt state. That's it. I don't know if that. I'll go into it anyway. So, like, how do you sort of think about these traffic lights? So, I guess this is more interesting if you're a contributor. So, when you publish a patch or a series to the mailing list, you get up. The build is being performed, and if you see this, so this is Charlie's example, for example, and it's not pointing out Charlie in any way, but it's we have in total 12 tests, and the 13th test is sort of the overall state of the whole build. So if for example, if you look at the right-hand side here, the top one stating like for the full pull request, that means that if any of the patches in the series fail or get a warning, you'll get red there. Or likewise, if you have a warning anywhere, you'll get a warning there. So, and again, like I'm not a UI guy, so we can probably improve this. I'm sure. But yeah, so for example, here for some reason it failed with a RV64 GCC build.
It's more for you. I'm around these ones, they're not that everywhere, but from like when like obviously some of those things have to get red lights for, I don't know, some silly patch related thing. Like how much do you actually go and look at it, see it as a red light and care, or like do you mind seeing red lights that are any enthusiastically red?
I don't know. I guess I mean the thing. Like it's kind of a tough one. Right now, because we're not doing boot checks, can't rely on CI. It's like the whole thing. If that makes sense. I gotta rely on testing. So yeah, basically I go through and if there's some red things, then I look and I see if it's something that looks scary. If it's not, I just ignore them. If we could get to the point where we're doing enough boot checks and enough build checks where like green, then it's good to go. I mean, read the code and stuff. Green means it's not going to fail any of the tests that we're doing. Then having like unreliable reds would probably be a problem. But for now, it's not.
Right.
Like, actually, I don't know.
Yeah.
I tell everybody to use it, and sometimes it kicks backwards stuff. So I don't know, we can all get that.
And there's a lot of I don't know. We could discuss like how strict we're gonna want to make check patch, for example, and if it's even interesting. I don't know. Running check patch on the org specific tend to generate a lot of weird warnings.
That's the problem, right? All this weird assembly stuff we do.
Exactly. So I don't know if it's a good idea or not, but it's. And I would go. This is just like sales slides more. It's like you can click into it and get a build log, and so you can figure out what went wrong. I won't skip the demo. The demo is like click that link and you can click around. Resources here. I guess maybe we should get into like the next steps here. So right now it's like 12 tests, but we would like to, or like the grand plan is having like something proper to release tests. So I based it on something like Palmer's release test. I don't know if that's, maybe it's the RISC-V release test. So I did the build matrices based on what Palmer does for every release, and it ends up with 144 builds, 216 boots, QEMU, and boots include drills down to a number of different boots, DT API, UEFI, different implementation of UEFIs. I don't know, I mean, it's a lot, and it sort of ties back to like this, how much should we deprecate things, because this will just explode and be a lot of work for the build bots. But yeah, next steps here, like we need to obviously perform or fix performance here, because with these VMs we pay when they're idle, so we need to make sure that the utilization is at a maximum. So yeah, so this is also, you know, things we can work on. But I guess let's land here. So, which is like, what do we want to see in this pre-merge? Like, is it sort of, does it make sense to release this? I know you have said, Paul, that you would like to see like a complete build and, you know, boot everything. And
I mean,
so,
it's tough, right? Because like that stuff I have is just a random collection of things. It's pain for me too.
yeah.
I suppose it's stuff every once in a while, so I never feel like I want to delete anything.
Yeah, and I think that's the only place where we actually, if I look around at the other CIs, they pretty much, you know, they build def config and that's it. So there's no.
Just building def config, we have whole is like alternative errata stuff.
Yeah.
Like mixed in, and just the simple configs miss all sorts of stuff. Now maybe that's because we should deprecate a bunch of things, but does I think that.
So like there's other architecture to boot the entire all the metrics, saying QV, non-QV, SK, non-TG.
Yeah.
So then the current status is just a KV direct boot, or like
The current status is that's just a cross build. So the current status is like 13 builds, but what we're working on is getting this up, and we're realizing that it's a lot of builds.
Yeah.
So we have that running internally on the GitLab thing, but it's.
And also like when you boot boost, you get to boost, like you have to keep pulling in like what the cycle, release cycle, or
Actually, as soon as the baseline moves, we rebuild everything.
no, I mean the like kernel moves for every release, but for the indicate 2 or the boot, we go to like the release.
All right. Okay, gotcha. No, so we're sort of we're pinning something. So we're not rebuilding the world. So it's like we pin, you know, certain EDK2, U-boot, whatever, but the actual kernel will. That's the only thing we'll keep moving.
Yeah, because way too many moving.
It is. Yeah, definitely. I mean, even with those pin, it's way too much. So.
Yep. And at some point, also we need to upgrade those.
Yeah, definitely. But that could be, for example, like bumping GCC and LLVL release and stuff like that. That could be like a monthly or less common thing, but still, there were questions in the back. Oh.
Regarding the first point on mail editors, we went to work on getting this simplified directory.
Yeah, that's where it came up. It's part of KPD now,
It's a bit hard to get those information from GitHub runners into the email. So like we're integrating on the user experience. But it should be published maybe in a month.
Cool.
So hopefully you guys will be able to review.
Yeah. You're the guy that working on KPD, right? At Meta.
Hi, my name is Meta. It's already in GitHub.
Yeah.
It's just what you need to activate it. What's hard is to get the info from the build logs, not from the GitHub itself.
Right.
So you have to have essentially structured logs.
Yeah, that's why we forked your work, because we're doing it per patch build. So when we pull in a series, we build each patch. So we have a structured log which we parse, which is nasty, but that's how we do it.
If you manage to get proper logs, you can get proper log and get there.
Yeah, and that's what we're doing in the our thing. But it's, you know, it's a regex pel, so it's.
We should probably talk outside of the room later on how you guys see it.
Yeah, definitely. Yeah, definitely. And it's just, you know, shout out to the Meta folks. It's good stuff. So, and it's saved a lot of work for me.
I was going to ask if you're testing multiple toolchain versions. I know we had a discussion just earlier about what's the oldest toolchain we support.
Right.
Is that something we should be testing?
Right now, we're just trying to pick like the latest stable on kernel.org for both LLVM and GCC. So that means, yeah, so the answer is no, we don't. What's that? I haven't. Right. Yeah. Okay, Snowball. All right, interesting. Oh. All right, yeah. Interesting. Snow Patch, thank you. I'll check it out. Yeah, that's, I don't have anything more. I guess it's, I mean.
Yeah, unless you have questions or anything.
I guess, I mean, at some, right now, we're using QEMU, like, again, not you, yeah. Yeah, but I mean, it's, I would prefer having, you know, proper hardware or real hardware, but then again, like, what boards, how many boards? So it's
Another set of variables.
exactly.
And for the patchwork, you just do the build, right? Or do you do the boot test for?
No, again, so right now only build, but the, like, in the work is doing boots. And well,
series or every patch in the series?
every patch. No, for the for the series. So we'll do first all the, like, simple tests or build tests just for the patches. So check for, you know, bisectability, and then the series part will do, that'll build for, like, the matrices that the Polymer has in the release test. So we can't do that for each patch. But still, I mean, even with that, that's why, like, we're waiting to put it out, because it's taking too long. So I mean, the latency between you, what like when a contributor submits a patch, when you get response, I don't know. Maybe that's up for discussion as well. Like, what is a reasonable get back? Is like a week if you publish a patch and you get build results a week later. I don't know. That's a week is fine.
No,
a week, yeah, yeah. I would say like a day is okay, but it's
if it's more than a day, like I'm gonna get.
Yeah, exactly. Yeah.
How long is it now?
Right now is 20 minutes per patch, and right now that's, you know, that's nothing. I mean, the one that we're running right now, the monster build thing, that's that's a long time.
Yeah, that takes hours for me.
Yeah.
So just 20 minutes, just the boot or just the build?
What?
For 20 minutes per patch, you said?
Yeah, that's the current one, just the builds.
Just the build.
Yeah.
Right? Once we add boot.
Yeah, builds and tests. So, you know, these check patches and like the 1 of the 13 checks.
Are you using incremental builds?
We're
Sort of.
yeah.
There's no use case for.
5 minutes. That's good.
But we
That's good. Yeah.
self-positive. On variable.
Right. Right.
One problem is that the arch stuff, like I was saying, arch stuff tends to touch a lot of headers. The arch patches tend to touch a lot of headers, and headers that like trigger everything to rebuild. So incremental builds, like when they work, they're great, but they fall apart. Even simple patches, if you touch one of the arch headers, you're basically building.
I mean, and we're doing the low hanging fruit, you know, CC cache and all that, but it's still, it's 20 minutes. It's for serious. It's much.
I think the original build scripts were like largely based on what NetDev was using. But I quite remember NetDev was doing that order of those. We were building the patch, then incrementally building the previous commit, and then incrementally building the commit again to get the actual warnings added. Like those second two builds were pretty quick, but the first one was on quite long. I'm not sure. When I was on my Jenkins, the first patch in the series would be like 20 minutes.
Yeah.
The second ones might be like significantly shorter, than 5 minutes or something. I'm not sure.
And we spend a lot of, I mean, most of the time we're spent on linking, actually. So
I'm not sure if with the GitHub version that there's a builds 2 patches in the series, the second patch is quicker or not.
it is. Yeah. So it's. You know.
You're spending all your time linking, do like overlaps or something, because that can go way faster.
Yeah, we can cover it offline, but if I remember in our case, we essentially view and save the artifacts into the product cache.
Right.
For using the base. And that's what we get, hoping that it's close enough to be serious.
Right. Oh, okay.
But we can.
Yeah.
You use use actual GitHub caching of your build directory. Yeah. Your own caching. Okay. So I have used it like 5 or 10 years, but GitHub caching is yeah. Okay. But that works. That's easier.
So, you also mentioned about the email contributors. I think you do that only if it fails. Right?
What was that?
You also mentioned about the emailing the contributors.
Yeah, we don't. There's support for it, but we don't. So the question is like, is that a good idea? Like, do people want more mails or I don't know?
If it fails, it's probably good to
Yeah.
get that email. Like if the patchwork CI fails,
Yeah.
that would be good one. Otherwise, kernel CI, is there a way to like kernel CI has its own stuff, so somewhere we have to distribute the load between kernel CI or the kernel CI does one thing and then.
Yeah, exactly. So I guess that's the question. That's the question like post-merge, pre-merge. Like how much do we want to do in the patchwork part and how much do we want to do in the pre-merge? And it's.
I was just going to ask if you had any more thoughts on that overlap because I see a good.
There's a lot of overlap. So yeah.
But there's more like kernel CI is not doing any of the pre-merge stuff. So
yeah.
Stuff's all great, but then kernel CI is doing native hardware, overlap, moving and stuff like that. So there's a lot of potential collaboration. There's not a ton of overlap. There's a lot of good collaboration. So do you have any ideas on where maybe we should look at where kind of merge the two together or collaborate?
Good one. Yeah, definitely collaborate. But let's what? Yeah.
You guys do pre-merge tests anywhere? Yeah.
It's all basically just taking and none of the pre-patch stuff either. It's just take a branch, build it.
Yeah.
But we are doing like the whole matrix of def configs plus compiler versions, all that kind of stuff. But that just becomes build infrastructure. The more builders you have, the more you can do.
Yeah. But doing it all pre-merge is big.
And then you add all the pre-merge stuff per patch, and you add
really cool.
another couple dimensions to the matrix.
Can we do the kernel CI for the pre-release stuff like on your next branch?
Yeah. Like when I push next kernel CI, it sends me an email hour like this.
But it's just on that. It's on whatever the latest committed branches. It's not doing the series pre-patch stuff.
But it does compiler versions and all that stuff, and it does boot tests. It's on hardware too. Which is nice. But then trying to get it all running pre-merge is just like crazy, right?
So I don't know, maybe it makes sense to add like all the configuration that you run, like for the release, moving that to the post-merge. I don't know.
I think we should do is we should look through the configs that I run and figure out if they make any sense anymore.
Yeah.
If they do, we should add them as like .config. I guess we should probably. So we should go to all the configs I run and see if they make any sense. Some of them are probably obsolete, right? Also ones that are not obsolete, we should add them as .config so other people can see them.
For the bird batch build version thing, I actually don't know how it works, but essentially normally just sending patches to the mailing list. There is a build bot that checks that.
Exactly, but this is the build bot. So yeah, exactly.
What tree, etc.
Yeah.
That's this.
Yeah. So there's no somebody builds it there, man.
Yeah, I never set up anything.
Yeah.
I don't have Patchwork.
Yeah.
I don't know who does
that. Exactly. So that's up to each subsystem. So.
I never did anything.
That's great.
You're on x86, so there's people who.
No, I'm on any application.
Yeah, but I mean, like there are people who care to test that stuff. And various other build bots that just do all the stuff. Like this is live living bugs.
It is, and I mean that's maybe that's not. I mean, there's definitely like could be consolidation work here, like all the subsystems doing their own thing, which is scraping things from patch.
On a subsystem like me, that's silly. I mean, everybody is just working.
Yeah. I mean.
Oh, we have time. Sorry. Yeah. We have like negative minutes. So.
This is the next slide. He'll share it. Cool.
Oh, there it is.
Hello.
Do we need to do something to make audio appear? It's blinking. You guys can see the same thing I see, right? Yeah.
Maybe I should turn off the background.
Do we need to push some buttons to make the audio from the laptop appear in the room?
Hello?
You can hear him? I can't hear him. Am I just crazy? Sometimes that happens.
Is the laptop connected to the mic?
That sounds like the room next door, though. I'm not 100% sure, though. Kind of early.
Is my mic working?
All right. I don't know if you can hear us, but hopefully we'll get it to work.
I see. Seems like the person who is in the BBB is able to hear me, and not
I've got a
people...
USB-C charger sitting around. Clem was using it because he didn't have any. Oh, you're not USB-C? I don't think that was me. No worries.
I think we got the controversial stuff.
And I need somebody to flip the page. Hello? I need some physically touch the laptop and flip the page.
You're gonna...
Okay, your audio should be good to go now. Remote. There we are.
Is my mic working? Okay. Yeah, and the slide is I'm able to flip the page now. Thank you for fixing it. So this page has about 20 pages, and I have no idea talking about 10-20 pages. I'm going to finish in by 5 or 7 minutes. So this is the top slide, and this is the only thing I really want to say. It's a proposal of porting trusted execution provisioning protocol on the RISC-V, which with better hardware support, which Sci5 has as a word guard. And one word I would like to add is I really need a support and help. If that's the only biggest message I really wanted to say in this plumbers. I really wish to be in the plumbers. I just was in the different conference last week and couldn't afford to traveling to US from Tokyo. So that's it. And this is some of the words. It's related to TEEP implementation, and I'm going to skip it. And the reason I started to, this is the use case of the TEEP, but I'm going to skip it. So the reason I going to talk is I was able to release the source code of the TIP protocol implementation on April 2023. And how it went is something wrote it on the presentation page. 1/3 of the below. It's kind of rant, but that's how it was. And so this is the going to the documentation from the for the implementation. It's tough, so I just going to be really briefly, and it's already 47. So 12:47 midnight in Tokyo. So TE is one kind of the special hardware assisting if you want to run something alongside with the Linux. And similar implementation, first time I saw was PlayStation 3 when I was working at the Sony Computer Entertainment. It had a secure boot and it had a game OS and was running a game application, but there was something else on the side in different memory space was doing something sensitive stuff. And similar implementation and different similar feature, but completely different implementation I saw was set-top box. And so I would like to have the similar implementation on RISC-V. Okay, and so how it might be implemented on the RISC-V will be has a RISC-V World Guard CPU, and also has a secure mode firmware. It's probably will be in the OpenSPI. It's just a proposal. It doesn't mean it have to be this way. And the initial implementation on RISC-V without the World Guard, we was using Keystone project, but on the right side, but I'm not sure we will be for the World Guard support. But on the left side is the regular Linux kernel and the TIP agent. Oh, and above is TIP typo on the slide is TAM server, and then the upper side is verifier. Oh, I could have a pointer. So and the right side is the where it has a implementation of the TIP protocol on the device side. So TRF is provide TEE API, which is defined by you could see the API specification at the global platform, and on top of that is has a TIP device box is where it has the TIP protocol implementation. Honestly, this way of the implementation makes it easier to run the other TEE application from ARM TrustZone or something, or Intel to the RISC-V. If people would like to have more application or usage from the other CPU, then it might be good. But honestly, considering a security, hiding the TIP device in little SM region or underneath the runtime or S mode region in the RISC-V side is more robust for the security. But for the beginning, this is how we did in our initial implementation, and this is the easiest way to support on RISC-V World Guard, but I'm not sure what to do in the future. Okay. And there's a GitHub, not the GitHub, but on the GitHub, we have a wiki page, which has a link to the repository and documentation, and also slightly reduced page of this slide. And how the TIP protocol works is written in from the page 10 to page 11. And I'm going to skip the explanation here. And yes. So if I go back, yes, and the assumption is these are the assumptions we did not really have a resource to implement fully properly. So it does need a secure boot to ensure that a binary on the secure side is not compromised from starting from a secure boot. That's why it's written here. And yes, and these are the use cases. I wrote it down, the use cases, because it's why it's a typical question is not a technical detail how you implement it, why it's important, and it's more like why it's used and why you need it. So automotive usage. These days, if you buy an extra option for the automotive, historically you go to the car dealer and the car dealer add some physically option gadget onto your dashboard or in the engine. But these days, if you pay to the car automotive company, you have a serial code flying from the server and installed to the car automotive, and you have a better quick charge rate or something, or OTA or some other feature. And similar for the network equipment. Network equipment, it requires firmware update as an OTA, or also it requires a certificate updates. And in some cases, you might want to disable the device if it's detected being compromised. And this is like if the company is making a surveillance camera or home camera devices, it's also the use cases. And also this is not that much widely noticed, but it's most of the heavy industry, it's how to be governed is being based on the contract. So and it might be, it's good to in the future have technically having a control by not with the security feature. And yeah, for the drone, it's pretty much the same as other embedded. And this is something it's not really did in my, our implementation is for the confidential computing. It's called, but it's just a kind of the confidential VM, which is guaranteeing technically that the hardware in the hardware, the host OS not able to read the guest OS. So the person who wants to host a virtual machine on the cloud, and technically you could assure that it's not able to read from the host OS vendor. But then you do have a question that you need to who you trust is going to shift from the host cloud vendor to the CPU vendor. But yeah, that's something it's possible. So yes, and these are some status at the IETF for the making the implementation for as a standard. Yes, and I think that's it about my talk. Any question? Or I'm in remote, so somebody may need to speak in the mic, or I really don't know how it's going to happen. Yes, I hear you. Yes.
Cool. All right. Hi. So do you have like an POC implementation? Because you talked about different things, including confidential VM, for which we have a complete separate different spec. So it's not sure, like, is this just the TP protocol you're talking about, or do you have a POC thing going on in a different way? Because we saw also Opti version of RISC-V landed in the mailing list a few months back. Have not heard anything from that.
For the other use cases, not with the last one for the VM, there are, if you go to the documentation on the GitHub, there are a binary installing just printing out hello T. But if you modify that code, yes, all the other infrastructure is working. But if it,
using Sci5's WorldGuard?
yes, it's working on Sci5. So initially, you could try on Docker on RISC-V. It should be working. If it's not, please let me know. Send me email. And
Can
if
you go back
have
to so what are you probably need some RISC-V specific specifications, right? Like how does the OS talk to the secure monitor you have?
The current implementation on RISC-V is only using PMP as a for the securing application on the TE side, which is not really enough for the security consideration. So which is compared to Intel SGX or TDX or RISC ARM Trust Zone, using PMP is really not enough. So
yes, so within RVI there is a working group coming up with like SMTTT with which basically built on top of WorldGuard, and then they have like domain IDs and all the stuff. Ravi is not here, but if you have looked at that spec and scope spec, and then how does this complement or with whatever you are talking about?
Yes. So right now on the left side, I should include the current implementation on RISC-V, which you're only using PMP for separating Linux and TE OS. But that's it's really, yeah. It's if you see the code, it's easy to come up with how to hack inside from Linux to the TE side.
Hey, accurate. One question.
Yes.
Do you expect the TOS to be running in M mode?
S mode.
S mode. If it's S mode, you may want to look at the SMMTT specification that Atish just mentioned, which allows you for protecting physical pages per domain. You would have a TE domain defined for your TOS. So if you're only expecting TOS to be running in S mode, this is really appropriate and doesn't rely on WorldGuard at all.
I see. That might be an option. Yes, I see.
And this is the same memory protection that we use for the overall RISC-V confidential computing specification, based on SMMTT, with other ABI constructs that you probably don't need, but at least for memory protection, if you're running on S mode, SMMTT is probably a good fit.
Okay. Yes. Thank you. Thank you for the input. Yes, I will look on it.
Yeah, cool. Thanks. Sorry about the audio issues, but hopefully we'll do better next year. I don't know. Totally different place. I can't promise anything.
It's all right.
Cool. All right. Thanks so much.
Thank you very much.
Yeah,
I wish I've been in Virginia sometime in the future.
Okay, so hi everyone. I'm Clément Léger from Rivos. I used to work on more exotic architecture, so I'm quite new to the RISC-V architecture. So please bear with me if I say silly things. I'll be talking about Supervisor Software Events Extension, which is the SBI extension. So why do we want to do that? So the SSE extension is much like Harm SDI, and it will allow us to inject mod to HS mod from higher privilege mod. And we need to inject high priority events which cannot be masked at all, and that can interrupt the kernel at any time. This can be used for reliability, availability, and serviceability errors, so RAS errors. And these one are errors that needs to be handled as fast as possible. We'll also be using that for the PMU overflow IRQs and also for power virtualized asynchronous page fault. So the SBI specification was sent by Himanshu and Hanup, and it's actually currently being discussed on the Tech PRS workgroup. So how do we plan to do that? So the SMod will actually register some event handlers, which will be called upon specific events by the SBI. And we have different types of events, local, global, events IDs. And upon these specific events, the SBI will actually divert the execution to replace the interrupted context with the SSE handler entry context and resume the execution at the specified handler entry. And upon SSE handler completion, the handler needs to call SBI call to complete and resume the execution. From a supervisor mod OS point of view, it's almost orthogonal to OS normal operation, which means that there is no impact at all on the normal execution of the system, and it does not use the regular interrupt path. It will use some specific SSE entry to handle that. It also avoid to wait too long, for instance, in the IRQs of section of the kernel to deliver the SSE event. The SSE event will be delivered right away because the interrupts that needs to be injected, let's say, by the SBI will be taken in M mode and will interrupt the kernel execution. So this can be seen as NMI. And it does not use so much OS-specific resources, except some memories and stacks, which will be allocated for each event. So amongst the problem, let's say, that's at least the question that we are currently studying, is the encoding of events. So events can be nested, and there are some priorities associated to these events. By default, it's the event ID which encodes the priority, and this ID 0 is the highest priority. So we discussed that with on the Tech PRS mailing list, and we try to find a scheme that allows to encode the priority in the event IDs. The best solution we came up with is to have the global events that are less that have a priority less than the local events, and the platform events will also be less prioritized than local events. But yeah, maybe some implementers might want to have platform events that are higher priority of the other ones. So if anybody has any ideas, not ideas, to encode that, you're welcome to participate. So the SSE context is made of a lot of general purpose registers, and we'll see that later. There are some questions about that, about how much register should we save. Is this a good idea to do that like this? But at least for the moment, the spec is using that. So which means that we will save the SBI will save a set of registers, of general purpose registers, when actually calling the SSE handler in SMod, which will allow you to nest SSE events on top of interrupts or whatever is currently executing. So quick pros, cons for SSE versus pseudo NMI. So currently a pseudo NMI series was submitted, which does not address everything that we want to address with SSE. One advantage of SSE is that it's a true enemy-like event. As I said, we can interrupt the kernel at any time, even during the exception path, really early in the execution path. It also allows to nest events on top of each other. We have a faster delivery time than standard IRQs, but to be confirmed, we'll see that in a later slide. Minimal modification of existing code base. I mean, the SSE support is purely in addition to what exists currently. We don't modify anything of the IRQs, masking, and so on. And it's easily extensible. It's pure software implementation, which will allow to add new events and whatever we want to the SSE system. One of the cons is that it requires SSE compatible SBI. So this means that if you are using a specific SBI, you will need to implement the SSE support, which can be quite tricky if you have some advanced preemption in the SBI implementation. And we'll see that later. There is also some additional work, let's say, to retrieve the current task struct in the RISC-V current port. For the pseudo NMI, one of the pros is that it does not require at all an SBI support, and a few parts of the interrupt handling needs to be modified. It's simpler than SSE, at least from what we saw, but the critical section in the kernel, so such as the exception handling, are still uninterruptible. We need to wait. At least it can be nested right away. It does not support nesting nor priority. At least it uses what is provided by the hardware. And there have been some performance loss measured for the existing use case. So this is from the series. You can look at that on the mailing list. So one of the biggest problem I'd say that I try to address is that, as I said, SSE can interrupt the kernel at any time, anywhere, and mainly during exception handling, which happens. Since we need the current task for accounting for preempt count and so on when entering the NMI path, we need to retrieve this current task. And this is a bit of a problem for us because the current task is stored in the CSR scratch. And at the beginning of the exception handling, we switch this CSR scratch register with TP. And depending if you were entering from kernel space or user space, the current task might be in CSR scratch or in TP, which is not really convenient for us to reliably get the current task. So we need a way to know exactly where is the current task located, and it's based on the address and on the previously executed context. I tried multiple things using address comparison, checking with labels inside the exception link path, which is quite unreliable and not really flexible. I also tried using labels instead of address, and finally it's also a bit fixed. And finally, the last thing that I decided to go with is to annotate the sources with fix-up-like data. So it kind of seemed like a huge thing to address this problem, but I haven't been able to come with a better idea yet. So the idea is to actually push some annotation into a specific section. And as you can see on the right side, there is only a few parts of the kernel that needs to be annotated with that. And then in the SSE handler part, we actually iterate through this task location, so current task location, to actually match the correct register in which the task struct is located. So we annotate the task with, so the first part is where is located the task struct when we are entering from SMod, and the second one is where is located the task struct for where we are entering from user mode. So depending on the lines, as I said, it might be located in either one or the other, and this is not cool. So clearly, if we had another scratch register, but this is a bit too late for that, it would have been much easier. Some of the problems that were raised on the mailing list is that this SBI extension creates a bond between the SBI specification and the RISC-V unprivileged ISA, because we have a struct that contains all the general purpose registers. So ARM went with some different way, is that they do not provide any binary structure to the SDI handler. They actually request the OS to call the SBI, at least not the SBI, but the trusted firmware implementation, to retrieve each registers. So this has an additional cost, and we'd like to avoid that. So that's why at least this specification addresses that, and it's quite efficient. But it restricts the set of registers that are saved when entering SSE handlers. So there have been some discussion. Potentially, we could save less general purpose registers, but I'm not sure it solves the problems of the cherry spec, which needs some additional CSR and things like this to be saved. So the cherry spec is quite big. It's like 400 pages. So I wasn't able to read everything, but at least Jessica Clark raised some problems on the mailing list with that. Some numbers with this implementation. So we have made a proof of concept, and RFC was sent, at least for the kernel part, on the kernel mailing list. We made a proof of concept with the PME overflow IRQs. We went from, so this is purely in terms of instruction executed, and with normal IRQ handling, we are at like 1,600 instructions executed. And with SSE event handling, we are at like 800 instructions. So this includes the mmod execution, of course. We don't have yet, and this is the next steps to be done, to gather more precise number using hardware platforms to measure the impact of caches and so on. One additional point of the SSE event is that we don't have any jitter due to interrupts being disabled. So which means that if you are executing in a section of the kernel where interrupts are disabled, you will have to wait for the interrupts to be re-enabled, for the interrupts to be, the PMU interrupts to be handled. So this can add, depending on your configuration, quite a few instructions. So the current status is that the implementation in the kernel is like 1,000 line of code, and similarly for OpenSBI. And the SBI extension is still in review and could be ratified in Q3 2024 for SBI v3. So do you have any ideas, remarks, feedback?
You mentioned that SSE sort of solves your jitter problem.
Yeah.
With does the pseudo NMI solution also solve your jitter problem because you aren't masking, you're only masking external interrupts, not the interrupt that would be injected here, or?
So with SSE, we actually don't modify interrupt status at all, but the interrupts are going to be handled in mmod, so they are going to be handled right away. I mean, it's not depending on the SMod state of the interrupts, so we don't have any jitter, as I said. So, and then the implementation itself is pure software, but the configuration, of course, of the interrupt delegation and so on is done in the SBI and relies on the hardware. Yeah.
But if you're doing pseudo NMI, you wouldn't be disabling interrupts either, right? Or
Yeah, pseudonym also solve the same problem by selectively disabling the mask, interrupt mask. The problem with is that affects all the workload, like anything you are running that basically adds the extra overhead while for switching those things. So that's why the slide says that 2% additional overhead for everything. But here it's selective, like it's first SSE is faster, and also you enable it only for why it gets kicked in when you are using perf compared to the pseudo NMI.
Okay, yeah, I guess I'm not super familiar with the pseudo NMI, but I would imagine like instead of like you can globally disable interrupts for S mode using the interrupt enable bit, and then you can like disable external interrupts using a different bit. So if pseudo NMI is just disabling external interrupts instead of globally, no.
It's also disabling the local interrupt, because this is a local interrupt. This is not an external interrupt. The overflow interrupt is it's a local major interrupt, local interrupt number 13. So you have to manage the entire interrupt mask with that.
Okay, so there's actually more registers that need to be modified with pseudo NMI. Okay,
that's why you see that 2% overhead.
Because like I would imagine like the easiest way to solve all of your ABI concerns with SSE is if you just inject an interrupt, use it from in mode, and then use the normal interrupt handling infrastructure.
But then you lose the benefit of being able to handle the interrupt right away. If the interrupts are disabled by the kernel, you will need to wait for the interrupts to be re-enabled.
Yeah, I wonder if there would be a way to not disable interrupts in the kernel, but probably not, because
You save and restore, right? So
and for instance, in the exception handling path, interrupts are disabled when entering them, and you can't re-enable interrupt right away because you would mess up the whole stack and you would overwrite the previous context. So that's why the pseudo NMI cannot interrupt the kernel at any time. I mean, in a few parts of the kernel, in the exception handling part, it won't be able to handle that. So this is, let's say, critical for mainly RAS errors, which are hardware reported errors that needs to be handled as fast as possible, because if you let the fault propagate, potentially you can mess up the whole kernel rather than offlining the page as soon as possible.
I guess question, can you software simulate any of this stuff so that we can get it in CI? The reason I ask is this sort of code tends to be notoriously fragile, and the events you're talking about are fairly rare because they're RAS events. So the mix of rare events and fragile code means that they tend to break over time. So having something in simulation so that we can put it in CI and make sure it doesn't break.
So exactly, the spec actually allows to inject the event from the S mod, but you won't be able to inject the event exactly where you want them to be injected, right? Because this is synchronous. So we have some asynchronous way to do so, because if a specific heart injects an event on another heart, then it will be delivered at a specific point of time, but you don't know which one. What I did to test some specific point of interruption is with Spike. I was actually being able to modify the MIP registers to generate an interrupt to the M mod, and then to request the M mod to inject the SSE event at that specific point of time. So what I did is, in the exception handling path, I just put a breakpoints, modify MIP, and request the M mod to inject the SSE event at this specific point. But you are right that the main problem with that is that you'd like to test approximately a lot of point of injection, which is not really possible right now.
Are there any interrupts that can, as you're executing the instructions themselves, cause other sort of RAS events that have to be handled? Because they're particularly nasty, nasty cases.
And there is for sure a lot of bugs remaining. Clearly.
So the ABI between supervisor and the M mode, is it tied to the SBI version, or is there a?
So you're right. The kind of the ABI is specified in the specification. So I guess this will evolve probably, and that's why I think maybe Jessica raised that point, is that we need to find a way to make this, let's say, which work all the time. and do not have to modify this because we need to add a register and so on. So
yeah, because I can totally see like for shadow stack and things like
yeah,
that, we'll have
that's what,
new
yeah.
contract.
This needs to be considered, and there are a lot of other specifications that might impact this one. So yeah, clearly we need feedback from, as you said, shadow stack, Cherry, and so on. Yeah.
These macros that I think you added that add this data into this different section,
yeah.
Is there a way to programmatically identify where those need to be added?
I'd like so, but at least from what I tested, what I looked at, it's really difficult to identify where it is located. How could we do that? I mean, you need to have the code location, exact point where it's switched, which context in which it is. So this is actually this that is, let's say, doing that in a programmatic way. I'm not sure. Maybe. Yeah.
Part of the problem here is that we're really abusing TP because we don't have TLS in the kernel. So this is sort of violating the ABI. So we need to write an ABI like a M and C mode equals kernel type ABI, where we're allowed to do this kind of stuff with TP. And then this is kind of dwarf. So imagine that sort of thing happening. That would be a lot of work. And it'd probably just be as buggy as what we have now, right? Like it's kind of chaos at a certain point.
I guess it depends on what you want to do with the information, but to a first approximation, basically any instruction that touches CSR scratch, which you can just look at the encoding of the instruction, is an instruction where you would need some sort of annotation.
Yeah, like at least tell all the places you might need one.
Right. Not necessarily what you need. But
Yeah, then the hard part is what is now in Scratch, right? And sometimes that's not even apparent from the code. You have to go figure out, all this other stuff, which who knows.
So yeah, fortunately, this is not everywhere in the kernel. We have only a small part of the code. Yeah, but this one is problematic. It's in the slow path of the SSE handling, but still.
Did you have any problem with finding your task struct when you're doing like a preemption of SSE events? So like you're already in an SSE handler, but you receive another SSE event?
Good question. Actually, it's not. I guess it works, but let me think about it. Why there is no problem with that? Is that
it's why we ended up with the sections, right? One of the bugs.
Oh.
But I guess you would have to like follow your PC back to see, oh, you're in an SSE handler,
exactly.
and then follow your PC back again.
So yeah, you're right. Actually, I found that because I tested with some, let's say, a large injection, a lot of injection, and at some point, I always ended up with a TP corrupted. So I had to do some execution trace with Spike, and it was actually quite useful to understand what was going on and see that my SSE event was actually interrupting the exception handling path at a specific path. I fixed a few lines and I was, okay, it works. And then I ran against the tests and it exploded. So I had to find where exactly the CSR scratch is modified. And fortunately, as I said, it's only in the exception handling path. After that, we can reliably say, okay, it's in TP, that's okay.
So their implementation does support preemption of like nesting of SSE events.
Yeah.
Or at least it doesn't crash in ways that we know.
Yeah.
Right? So, sure. But that's part of the reason we ended up with this, right? Because if you're trying to do PCE backtracing stuff, you kind of end up with the same, no debug info PCE backtracing stuff. If you're trying to backtrace PCs through exception entry, you're just in for a bad time. Yeah. So, hence annotations, right?
Yeah, and backtrace is also supported in SSE event. Because in SSE we switch the stack, so we also construct some dummy stack frame before entering SSE event handlers, and then we can have a correct backtrace.
Cool. So I think like 1 minute or something. Oh, you want to talk?
Yeah. Just more of a feedback required, or rather than question. So we're going to use this one once the spec is ratified. We're going to use this one for POR and to enable critical section profiling where interrupts is disabled. So it's a bit of a different what other architecture does for perf. So where M mode takes the interrupt first, then injects this event. So if when you have any concern, like it will break, like as of now, it doesn't break from whatever testing we are doing. But if you think it will break some use case that we have not covered, so please shout here or at the mailing list. Yeah.
Yeah.
And yep. And also like whether we should enable it by default or we should have a choice in config saying if you want critical section profiling, then use SSE. Otherwise, don't use SSE because it's kind of a scary path. Like it's fast, yes, of course, but it's a kind of scary path where your M mode gets a lot of control to get into the S mode. So and direct injection bypassing all the interrupt and entire interrupt hierarchy, hierarchy domains, everything in kernel. So yeah, it's kind of related. So I'll just switch. Yeah, it's also about perf. So. Okay. So the next one is basically talking about a bunch of perf things that are being implemented right now. We'll send patches for RISC-V, how things are being improved. One of those was basically SSE, where we'll change the critical section to enable the critical section profiling. We'll change it to SSE and M mode being injecting event. So as I said, if you see any kind of issues with that kind of direct approach, please shout. So other things, I'll just go over a brief introduction, like what exactly exists today and how it works. Just so we have SPI PMU extension with ESCO PMF that enables perf stat and sampling usage. That's currently enabled in kernel. So none of the hardware actually implements ESCO PMF, but Andis and T had some different version of ESCO PMF where your some register is different or your interrupt number is different. So it just relies on the alternate framework to patch that. And since none of the ISA extension until this point was actually able to access all the counter CSR, configure all the MHPM event CSR in S mode, what we're relying on is SPI PMU extension and the firmware having a map of all the event encoding and counter mapping through device tree. And that device tree node was only accessible through firmware. So that's why that's how it will let kernel know where are the mappings and encodings. Now, with a bunch of extensions that are being currently review complete, need to be ratified, is counter delegation, which enables your Linux kernel to directly access everything in S mode without touching SPI PMU. But apart from if you want to use firmware counter, if you want to use firmware profiling. So for generic hardware profiling, hardware counter profiling, you don't need to do any SPI PMU, and you can use these ISA extensions. But with that, there brings bunch of problems, which I'm going to talk about. One is we have this, we need to make it backward compatible. So we have now this bunch of checks where, okay, you see first, if the ISA extension is there, use this, otherwise use the SPI PMU. So that static key thing is all over the driver now. Then next is how do you discover the event encoding and counter mapping. So basically, when I say event to counter mapping, is we have 29 programmable events, and then we have bunch of 29 programmable counters, and I don't know, every vendor implements thousands of events. So we need to have a map which events can be monitored by which counters. So the problem in RISC-V land is we don't have any architectural events apart from cycle and instructions. So the cycle and instructions are only, also they don't support sampling. So what is recommended by the ISA or like RVA, by the ISA and RVA community is every vendor will use some programmable counter to also monitor cycle and instruction apart from the counter 0 and 2 for cycle and instruction to enable sampling. So now we need to have that counter mask for those events, because now your cycle also can be monitored by regular cycle and instruction counter, which is like 0 and 2, also some programmable counter which enables you sampling. So we need to pass that information to the driver so that it uses that. And that's where the generic notion of how ARM64 does the event to counter mapping doesn't hold anymore, because we can't do all to all mapping in RISC-V. And it's kind of also, we try to discuss that in the RVI SIG, and none of the community members agreed to that scheme. So what eventually we ended up, I don't know if can you see the image, how small it is there. Yeah. But so what I did basically, current proposal is two things. One is introduce a field in the JSON, which is called like counter ID mask, so that the perf tool can pass that mask, put it in a config too, and pass that to the driver. So I don't know if I can zoom it. Can I zoom it? It's fine.
There is a way to zoom it. I just don't know. So
I don't know if it's
probably fine. Yeah.
Is it better?
Yeah.
Yeah.
It's bigger.
It's okay. Okay. Anyways, so the couple of issues that we have is so I'm adding this one, which none of the other architecture do. Then if you use this, then everything becomes raw event. There is no standard event anymore. We don't have any predefined event in sysfs, unlike other architectures do. So for any standard events like cycle or instruction or cache events, everything gets renamed in a JSON file. So this JSON file is basically for KMU. So now we have a JSON file or for KMU events that renames the existing cycle and instructions. So if you do like perf CPU cycles, it won't work anymore because now everything has to be a raw event, and everything has to be passed from the JSON. And JSON, the JSON file, if I have the same event name, it will basically conflict with the perf standard events. So I don't know if it's a best way to do it. Probably there should be a way to in perf tool, there's a map of this is my perf standard event, map it to this event defined by in the JSON. That's required because every vendor will have these cycle and instruction events and some of the standard cache events mapped to some other counter, some other encoding, because we don't have usually all these basic events, all other architectures have standard encoding space, standard encoding for events. We don't have that. So this is one problem. So any feedback on this? Not getting rid of device tree binding. So kernel, we don't use the device tree binding anyways. So device tree binding is only for the firmware. So if any hardware has these extensions, it will not use SBI PMU at all. So there is no device tree binding in place. But I'm sure like will be ratified probably this year, or sometime next year. So we have to support a bunch of hardwares until this gets into the hardware. So SBI PMU will still be used, but for the newer hardwares with this extension, you don't need the SBI.
So the plan is not to do have SBI PMU also just do everything as a raw event either? Like
everything happens in driver, no SBI PMU gets called unless you want to use firmware counters, which is just a logical.
But for hardware that doesn't support these IC extensions, it does need to use SBI PMU.
Yeah, that's why I said in the beginning. Now, if you see the driver, I'll send the patch probably this week, which has like now a bunch of static key checks where it says if IC extension is preferred, because that's the optimized way to do it with minimizing the traps. So if IC extension is there, use this, access the CSRs, otherwise make the SBI call whenever you want to configure, do the counter configurations.
And I don't want to spend too much time, but I guess my question is so for the interface between the driver and SBI, right? There's the standard extensions and there's the standard events and the raw events. Is the intention to have that interface always use raw events or continue to have the mapping that we do in firmware so you can use the standard SBI?
No firmware interaction, nothing. Nothing comes from the firmware because we want to have everything in S mode and manage the JSON file in the firmware in the S mode. Part of the reason also is eventually we'll have ACPI only, so no firmware will not have any device tree. So then it also saves the burden of firmware supporting SBI PMU extension, which don't care about SBI PMU at all, where hardwares have the counter delegation. But for existing things, it will continue to work.
So is the intention not to support the SBI PMU extension for hardware that does implement these IC extensions?
Yes.
So so breaking compatibility with existing software that assumes the existence.
No, it will not break. At runtime, you detect, and then there's no backward compatibility break. At runtime, you detect whether you have IC extensions. If you have, then use it. Otherwise, fall back to the SBI PMU extension if the firmware supports it.
Hi, can you hear me?
Yeah.
Hey, I'm trying to understand here. You're saying, hey, you have 2 cycle events One is like the free running kind of cycle event, and the other one is you can use it to do perf record and profiling.
So
and,
this
and you're trying to find a way to abstract this in the JSON.
yes,
And
because
why do you put the counter? I've never seen this before. The way it's done usually is you invent an encoding. You create an encoding that is not a hardware encoding, and the kernel will recognize that special event code, and then say, oh, you want that special version of the cycle, and he will program it on the correct counter. Right?
That's yes,
the way it's done.
That's the way it's done, because if
Not
you
this you're saying, hey, I want you name the counter. It's
Yeah.
not the way perfect event
I agree.
works.
That's why I said it's probably
That's
not
my
the best
feedback.
solution.
That's my feedback.
Yeah, no, I agree. The reason I wanted did this way at the first version is to enable that counter ID mask, because I don't know whether the cycle is mapped to which counter for that vendor.
That's a different problem. You're talking about the ref the generic event called cycle.
Yes.
That one, it goes through the perf tool. It passed as a generic cycle event, and the kernel does the mapping from that one to whatever the hardware defines
Correct.
for it. But it's in the kernel. It's not in the tool. The encoding pass for cycle is encoding 0 or something like this.
Yeah.
It's a hardware. It's called a hardware PMU event, and it's mapped into the kernel and the table that the kernel defines for each CPU model.
Yep. So if you just want to do the stat on like how many cycles or how many instruction, you can still use the 0 and 2, like whatever the hardware. For. This is for to enable profiling on those
Then
one,
in
because
your case, it seems like you need to have a different event. You say, hey, I want a cycle, the cycle free running or the cycle,
Yes.
The regular
we
cycle.
we can
And
do
then-
that way,
and
saying.
I can see your problem at the, hey, what about the generic event called cycle?
So currently what my implementation does, at least for the first version of the driver, is check if it is this cycle executed event, and if the user requested profiling. If the user has not requested profiling, like if you are doing perf stat, it just defaults to the counter 0, because that's mandatory.
It can be transparent to the user.
It is transparent to user. It's just that this ABI, not ABI basically, but the name change which is weird. What we can do is we can have like a different event, and then cycle instruction remains to be only stat. Then there's a different event name, but then user gets confused. If I can do profiling on cycles, but I can do profiling on cycle dash something.
No, I think if you hide it behind the generic event, it's probably okay. You just need to make sure that the two count the same thing. Is that the case?
That's the hardware's responsibility to make sure that they count the same thing.
The same thing.
Yeah. Ian has a question.
Yeah, no, it sounded like you were changing the event discovery code, and having different event discovery on RISC-V versus everything else would be a pain in the ass. So the legacy events, the cache and the cycles and instructions and so on, yeah, they use a PMU type that's never used.
Mhm.
The low ones, except Intel has a habit of using raw, which is 4, and overloading that. But yeah, having two different discovery mechanisms for RISC-V and everything else, the problem is that we'd always break you because we have no. At the moment, it's very difficult to test RISC-V.
Agreed. So what's the best? What's the other alternative solution? If we can find mapping between the standard event to a vendor specific name, that's the best thing. What's the next best thing looking for? Like, how do we solve this one to where we can also provide the counter mask?
To Stefan's point, it's like just always hacking it in the kernel driver. It's the way it's done at the moment. The legacy events, they're not really going anywhere, and we just added a whole bunch of like big little hybrid support for them.
Okay.
So if RISC-V doesn't support them, it's not going to support a whole bunch of things, and it's going to completely change how event discovery works, and it's going to break as a consequence.
Okay. We'll try to see how do we do the driver without changing this one. So this was basically the next problem is counter mapping. So x86 does, so ARM64 does allow to, all-to-all mapping. x86 has a bunch of constraints with all the CPU model specific constraints being applied on those. We'll have much more bigger problem because now we have every vendor will have different constraints. So we can go that route. So it's easier to just have the JSON file infrastructure where vendors can just update whatever the counter constraint they want to put in without not to break anything, I chose config 2, but I'm all ears. What's the best alternative to use this one? So I basically map counter ID mask, which is specified in the JSON, to config 2. x86, I noticed that the Perfmon repo and all the JSON file has a counter field, but I didn't see any kernel being used anywhere. It has like a comma separated counter IDs, mostly used for SMT, non-SMT hybrid cases, but the perf doesn't actually pass that information. So is there a better alternative or standard way to do it?
Waylin Wang at Intel, she has a patch set up. Oh, Waylin. So adding the counters into the JSON and using it in the tool. We'll be talking a bit about it on the Wednesday talk in the main track.
Okay, yeah. If we can abstract this to have for other architectures, so that's the best thing we can do, because for now it's just a RISC-V which I don't like. The other thing, the problematic, I don't know whether the problem or whether we need this. x86 has a bunch of this encoding scheme, right? Event encoding where your edge, inverse mask, counter mask, all those things. And then these are all standardized in the format attribute in x86 code. We don't have any standard encoding, so we'll end up vendor specific encoding. So as of now, there is no provision for it, but is that like actually gets, I wanted to know how much it gets used in place, and do we need to provide anything? I don't know whether we'll come up with a vendor specific scheme. Vendor will need it, and we have to provide a vendor specific scheme. But looking at x86, I saw some usage, but didn't know how much it's in actual usage.
I think you're out of time too.
Oh, okay.
Unless I got the times wrong, I'll check real quick.
Yeah, there's an obscure reverse use case where we use what's in the encoding fields to work out what are the valid bits in the config. And so if you use config bits which aren't part of a format encoding, you get a warning.
Okay.
Yeah.
Okay. Yeah. Thanks. I'll sync up with you guys later. Okay. Where's the vector? Yeah.
Okay, hi, it's Andy, and I'm going to talk about RISC-V Vector, what is the current development status, and what we're going to do next. Okay, long size, it might be a little bit small, but I will go through what is the current status. We now support running vector in the user mode, and context switch is it's happening on the context switch itself. It's not the legacy style x86 lazy save restore. And we support ptrace and signal interface. And what is in development is the kernel mode vector part. And now we support running kernel mode with and without preemption. And the patch is on the list. It is in V3, and in V4 we're going to introduce memory copy, man set, man move, and copy from copy to user with vectorized function variant. Yeah, and there are some challenge in kernel mode vector, like if we blindly enable kernel mode vector, it actually does not lead to the optimal performance. Like we can in an FPGA setup, we run Hackbench and NetPerf, and Hackbench it's launched like thousands of process and do small copy around 100 byte copy through pipe. So we actually see 15% of regression if we just blindly enable vector. And for NetPerf, it is better because NetPerf, there are a lot of large copy involved in NetPerf. So we can see when we blindly enable vector for those operations, we see around 54% improvements. Yeah. So there are several reasons we are now that vector just blindly enable vector will not lead to optimal performance. First is that there are hardware performance characteristic difference, and there are some vector tear down and startup code that is when Scala is doing the main copy, it's actually copying memory, but while vector are doing the maintenance code to start and to enable and disable vector unit and stuff like that. So currently we do enable a vector in this following step. We first check if this is in hard IRQ context. If yes, then if not, then we enable vector. And first we save the user mode vector context, and then we use a per CPU variable to keep track of vector unit and enable vector. And I do some approach to improve this, but I'm not proposing this because it might be some problem and hard maintenance. Maintenance cost may be harder, and so the main improvement from this is I do enable vector by default after booting and enable vector in unit when we enter trap. And other things is like we can use a thread flag instead of using per CPU variable, because per CPU variable costs a little bit higher to do vector enable and disable. And this is a flat plot before optimizing and after optimizing kernel mode vector begin, and we can see that it's around 100 cycles improvement to do main copy. And so the reason why vector may not be better than Scala is the first part of the plot. We can see that when the n is very small, the copy size is very small, then at this time vector is not doing a better job with comparing to Scala. And we can see we can try to calculate when the vector is perform better than Scala, and do a mod and only do vector copy in the when the size is larger. And this is a result of previous plot like Hackbench and NetPerf. If we only enable vector for the optimal size for vector, then we can see actually there's not very much different on the on large copy size, because the constant cost is being hidden. And but for a small size copy, we see less performance regression when we use optimal size for vector. And so I think we should only enable vector for larger size if we want to do kernel mode vector, and maybe add a DT interface for vendors to give a number of their optimal size. Yeah, and if anybody have any opinion about that?
I see you want to use the size to determine which version of the memory copy to use. But and I also see you judgment on that if the size is larger, you will get a better benefit from the vector version. But my question is if the DDR bandwidth is not high enough, that cannot support your measurement, because your measurement is based on FPGA, and in the FPGA scenario, it could give you sufficient DDR bandwidth.
Yeah.
So that's where you got that result. But in the real tap out the chips, I think depends on different scenarios. It maybe for the server, you could gain a high bandwidth with the external DRAM, but for some embedded scenarios, that's a limited bandwidth scenario. So maybe that vector version would be deprecated a lot. So what I proposal here is, could we consider different ABI version to this memory copy? I mean, the vector memory copy or the normal regular memory copy?
I think that will be a little bit complicated when because users don't know what sometimes the size is variable, but I can see that this is strongly related to memory bandwidth, and actually we in FPGA we simulate the bandwidth. We have memory delay module and we set it to around 85 nanosecond LLC miss penalty, and we simulated this core running on an 2 gigahertz platform, and so I think it is vendor can decide what size what is the size optimal size for their memory bandwidth and for their core, and if some vendor have less memory bandwidth, then they can do set it to a very large size and only enable vector after that the size. Yeah.
I missed what you said you're doing with user space vector. Are you doing any lazy restore at the moment? Or?
You mean we the lazy save restore in user space?
With context switches, yeah.
In kernel, we are not using lazy save restore to user space, and
So you just restore every.
no, we actually we restore before we really want to return to user space. We have a deferred restore mechanism in kernel. So if we enable kernel mode vector multiple times, we only have to save at the first save user space vector context at the first enablement of vector unit, and we only restore before we really want to like return to user space.
Does it make sense to try to detect the boundary for vector versus scalar performance at runtime?
Do you mean the enable of vector?
Yeah, you're talking about like the vector mem copy. You only want to use it for larger sizes. Does it make sense to try to detect that boundary, or like a good approximation of that at runtime, so you don't have to worry on like what's the device tree binding, or how do you do that for ACPI?
Right, that is a good idea, maybe, but it will lead to increased boot time, and I think it is easy to determine the slope and the constant characteristic of the loss plot, because they are all linear, and we can yeah, it is doable, but I don't know others' opinions about this.
Probably depends on the variance in the break between the vendors, right? Like if we're talking about like 32 or 64 bytes, then like maybe it doesn't matter and you don't need to measure that breaking point. But if it's some sort of huge like range, then you'd get more benefit from doing the dynamic
exactly
check.
Yeah, so an easy way is to just set it to 1K or 2K.
And I guess even worse, it could theoretically depend on OPP points if the CPU point changes. But I don't know how complicated we want to be.
I just wanted to, like, at runtime detection, we have to be careful. Now we are doing fast, like unaligned access at runtime. So how much boot time also we are costing there, right? So
yeah, so we can do an analysis about the size of main copy, and I actually do that. Most of the size is very small for boot time, and when we enter user space, there are a lot of page faults, and page faults there are a lot of kilobyte copy involved in page faults. Yeah.
I'm Deepak. I do security at Rivos, and today we're going to talk about control flow integrity on RISC-V. This is what I've been doing for almost 1 year, and there are a bunch of people working on this stuff. So basically, I'm kind of representing everyone's work. Yeah, so we will talk about the basic problem statement and then the path we are taking for enabling, and then we can take questions. I'll try to run through them as quickly as possible. Memory safety is one of the major issues for C, C++ code base, and they are vulnerable to corruption. And I have provided the links to that from notable researchers on the topic. And one of the major implication of memory safety issues is that you have your function pointers or virtual function pointer table and read-write memory, as well as your return addresses on the stack, which is read-write memory. And if you have a memory corruption in hands of an attacker, they can corrupt those addresses and then take control of the program. Most of the other architectures have similar primitives, which allows to protect these control flows. And on RISC-V, we started with ZI CFI name, but then we have split into two different extensions now. So one of them is ZI CFI LP, stands for Control Flow Integrity Landing Pad. It protects the forward control flow. What it does is that it enforces all the indirect branches must land on a landing pad instruction. Otherwise, CPU is going to fault. Except when RS1 is X1, X5, or X7, they are usually the sequences in the code that is basically used to do something like AUIPC, X7 offset, and then do a JLR X7. These kind of sequences are basically immutable because it is not relying on memory loads. So they are exempted from requiring a landing pad on the target. And the other thing that architecture proposes is that when you are landing on a target, you must have a label setup, which will be set up on the call side, and on the target, the label is embedded into the LPAD instruction, which is proposed here. And if they don't match, CPU is going to raise a fault. We call it software check exception, and it is a new cause code. The spec is not ratified; it is still in development, but this is the direction that it's going right now. ZI CFI SS extends the architecture with shadow stack. Existing encoding of 010, which is reserved, is used to mark the shadow stack. Shadow stack is a memory which we want to be to have writes allowed for storing the return addresses, but nothing else. So regular stores are not allowed. Regular loads are allowed because you want to do things like backtrace. So you have an area using which you can do the backtrace reliably, knowing that there wasn't any corruption. Shadow stack memory accesses strictly operate on shadow stack memory. So if for some reason, due to some error in the program, a shadow stack instruction executed on read-only memory, that will result into a store page fault. We'll get to that later. If a shadow stack access happened on a read-write memory or a read-write execute memory or execute-only memory, that will raise an access fault because a program should not have any need to do that, and that indicates a fatality. And the way, if you can see this, you guys can see the short sequence of code that I've written over there, right? So when you compile the program, can you see that, or do you want me to zoom into it? What? Yeah. Oh.
I mean, your slides are in a, I think it's in the speaker view mode or something.
Can you come here and check?
I have to upload the PDF again. So.
The PDF is right there.
No, that PDF itself I'm seeing is in the speaker view mode or something, so it's not full screen. Because I see the same thing. I don't see a different one. Oh. Little
Okay.
better.
Better? Did I do?
I can see it. I'm in the front, but who is in the back? You can see it. I can see it.
Okay, cool. So yeah, when you compile the program, compiler is going to generate this kind of prologue. You have landing pad first, and then you have SS push X1. SS push is basically pushing your the value which is in X1 onto the shadow stack, and your shadow stack is implicitly in a new CSR. It's called as CSR underscore SSP. So that's kind of a new general purpose register, you can say. When in the epilogue, when you are returning, you load the return address in X5, and then you do SS pop check X5. This instruction does is whatever is in the X5, it pops from the current regular stack, and if they don't match, it's going to raise a software check exception with a TVAL saying that it was a shadow stack mismatch kind of a control flow integrity fault. If they matches, then you can just do a JRX5, and that's how shadow stack work. Shadow stack and page fault. If we go back to one of the previous slide, I said that shadow stack access raises a store fault on a read-only memory. And the reason for that is that when we do fork, kernel has to make everything read-only, including your regular stack pages. And it does cow based on whenever a write access is done on those pages. The same kernel is not going to make an exception for shadow stack pages. So kernel will make them read-only, which means that in PTs, they will be read-only marking. But we still want to allow the subsequent SS pop or SS push, SS pop check or SS push that are happening in the user mode. And in order for that to allow, we want to get a page fault and not an access fault. And that's the reason read-only memory, whenever a shadow stack access is happening, we raise a store page fault. And the reason for store page fault is that any shadow stack access in user mode means that at that point of time, we want to do a copy on write for that page. Yeah, I think this got talked about. Now coming to the runtime control flow changes and CFI. So these are the things that I could enumerate. If you have anything that I missed, please let me know. One is text patching, and within text patching, we have tracing, breakpoints, setup probes, and of course, eBPF. eBPF, I didn't find anything which wouldn't work with this scheme of things, as long as whenever we are doing the JIT code gen, if BPF program, if the code gen is updated to emit the shadow stack sequences and landing pad sequences, it should work. BPF program attaching to the K probes will work as long as we make sure that K probes are working. Is it still?
Yeah.
Tracing.
Yes, question
Go ahead.
here. So you're talking about protecting the shadow stack need to be protected, right? Because it is marked as read-only memory, right?
Right.
Otherwise, the security property doesn't make sense. How does that, but also it allows some special instruction to access, to write, to read shadow stack, right?
Right.
I'm wondering what is the CPU state, right, or additional bits you are using in the page table entries to ensure that the CPU knows, okay, this is a shadow.
Yeah, so it's
stack.
010. RWX is equal to 010. So write bit is 1, read bit is 0, execute bit is 0. It is in RISC-V that is currently a reserved encoding. So if you have that encoding, it's going to be a fault anyways. When you implement this extension, then this encoding basically tells the CPU that this is a shadow stack page.
Have you thought about anything about the virtualization? Is that hypervisor is going to be confused on this encodings?
So
Or you need to do
for
special.
second page tables, this is anyways reserved today. But yes, if we want to protect supervisor shadow stack using H extension, that might come in the future, and in that case, we can try to see what we can do for against aliasing attacks against shadow stack. But that's not part of this spec yet. This is
Thanks.
There was a yes, probing and sorry, tracing support and CFI. So a prologue with CFI would look like something like this, in which usually when we enable ftrace, we have knobs inserted at the call location, and those knobs are updated with AUIPC, the register, and then we do a JLR to that register, which is basically a trace handler. With the CFI, the prologue will look something like in which we have a landing pad inserted at the target, and then we have the AUIPC and JLR. Current proposal that we are doing is that because landing pad is going to check the immutability of the control flow, the landing pad itself cannot be patched, but the knob subsequent to that can be patched, and that's how we are rolling with it. Breakpoints and text patch. So whenever we are going to put the breakpoints at the start of the function, if we are patching LPAD, then that's gonna basically raise the fault. Let's say if you replace LPAD with eBreak, eBreak is not a valid landing point and it's gonna fault. So the proposal is that if you're using GDB and you're trying to patch the target function using that, make sure that LPAD is never patched and the subsequent instruction is patched in the target location. With this in place, I don't see any issues that K-probes won't work. I looked at the KRAT probe as well. What KRAT probe does is it installs a K-probe on the function entry, and at that point of time, it makes sure that the PT-REDS array is pointing to their red hook trampoline. The red hook trampoline gets called, and it got the red probes, and eventually it does a JR2 array. And all of this should work naturally with the CFI LP and CFI SS. Okay, memory manager and shadow stack. So that's where we probably need some, eyeballs as well. So far, what I have looked is on the user mode, we have protection read, protection write. And whenever mmap issues a protection write, internally, what kernel does is it converts into a VMA of VMA read or with VM write. My current implementation creates a new protection flag called as prot shadow stack. And what we do is whenever prot shadow stack comes to the kernel, what we do is for the VMA, we set just VM write and not VM read. And we are treating VM underscore write VMA flag as the shadow stack encoding. Other architectures have used VM arch underscore 5, but they have their own quirks to that. We don't have any issues using VM underscore write. If you see any issues with that, yeah, let me know. Other thing is that other architectures, because they are using VMArch bits, they can't make it work on 32-bit because VMArch lives in the high VMA flags, and VM flags in the structure is 32-bit on 32-bit architecture and 64-bit on 64-bit architectures. Yep. Okay. The other thing that I wanted to talk about is shadow stack is dedicated to store the return addresses, but maybe it's not worth to expose the protection flag prot underscore shadow stack to the user mode. So right now, the direction I'm choosing is that what x86 has already taken. They have created a new system called as map underscore shadow stack, which implicitly assumes that this is going to map a shadow stack. So we don't need to expose this flag. And it kind of brings some security properties as well, that you can't arbitrarily manufacture shadow stacks using mmap and protect. User mode enabling. There are two paths here. One is we ld.so starts the life without shadow stack and landing pad, and that's the path x86 has chosen. But they have as far as I can tell, it looks like they have chosen that path to clean up their own mess. I'm still investigating. The other path is ld.so starts the life without shadow stack and landing pad. The only difference is when you are starting life without shadow stack and landing pad, then loader has to go and check all the objects in the address space. They have to check all the objects in the address space, and if all of them conform to the CFI, then it enables it using some PRCTLs. The other path is when ld.so starts the life with shadow stack and landing pad. In that case, also it has to check, but if it sees that any object is not conforming to the CFI, then it sends a PRCTL to disable CFI. This is still in progress, but the left is the chosen path right now. This is my last slide. glibc enabling. So some applications may want to disable CFI, so we need an option in glibc using which we can disable it. Some applications may want CFI, but they want some mechanism using which they can tell that if some of the other object files don't conform to CFI, don't crash my application, or don't still allow it to run. So we call it permissive mode. And then we can have a strict mode in which an application can say using glibc enables that, I want my application to run with CFI properties, and if any of the object file is not conforming to those properties, just don't run it. So we are following pretty much the tunables path that x86 has taken here, and that's it. Questions?
We only have 5 minutes.
How does long jump work? Like set jump, long jump?
So set jump, long jump will basically have to save the. It's kind of a set similar to set context and make context ABI. So in case of set jump, you're basically you can push that address that you want to go back to using shadow stack. So you'll have to update that in the set jump API.
There's like an SS save or something?
Something like that, yes. Okay. I mean, that's how I have envisioned it right now, because there is no landing pad there, so you can't actually, or you can, the other way is we can do is software guarded jump there, because we have a way to, but that is kind of a corruptible path because you don't have a place to store that, right? So you have, like, when you did the set jump and when you did the long jump, in between, if that can be corrupted, that's a window that you're giving an attacker to. But if you're storing that somewhere on non-corruptible area like shadow stack, then you have a better way to reach that path. I mean, there are a lot of more quirks, but I think 20 minutes is too less. So please talk to me if you want to talk to me about how we are going to safely switch the shadow stacks, because we have a mechanism of token switching as well.
I remember, I think there was an LWN article a while ago about CREU and shadow stacks. Were those issues ever resolved?
Those issues have been resolved in a way that CREU has to do its own way, do its own stuff. The only problem with CREU was that x86 shadow stack does not by default allow you to write to the shadow stack from user mode. So there is a bit in some of the x86 MSRs. If you light that bit up, it allows you to write to the shadow stack.
Okay, but it doesn't affect us then, basically.
It doesn't affect us because we are RISC, so we right size everything and rely on toolchains and compilers to do the right things.
On slide 9, you're talking about kret prob. And my use case is more in user space. So I have a tool that can do tracing of entry and exit of function by staying in user space without edit breakpoints. And shadow stack has been a pain for me on x86 already. And I'm wondering if this technique that you mentioned for kret prob can be applied also in user space in some way. Or is there a restriction with the instruction? I don't know the instruction set of RISC-V, so.
Yes. So in for your case, you will also install a retro similar to how retro is installed on the kernel, right?
Okay.
Or is
so-
it like in the middle of the function?
Okay, so that will work also in
That will work, because the major difference between shadow stack of RISC-V and other architectures is that other architectures implicitly push the return address on the stack. Here we have a specific instruction. Sorry.
Thank you.
Everybody, I'm Drew, and oh, good, I can see the slides here. Should I just press when I want to change the slide myself? Perfect. Okay, so I'm going to talk about IRQ bypass for RISC-V, which is something I started poking at a little while ago. Apologies for the slides looking a little overdressed. I actually created a slide deck for a different venue a couple months ago, and I just kind of stole stuff from there. But don't worry, the main slide has no color and hard to read. It'll be hard to read as well. So, all right. So first, I'll just go through really quickly IRQ bypass and also what RISC-V architecture offers with regard to IRQ bypass. And then I've got one slide which we'll speak to for the rest of the time. So for those of you that aren't familiar with it, I've got kind of this family here. We've got no device assignment at all on the left. And then you have a device assignment where you don't have IRQ bypass. And so here you still have the hypervisor in the middle injecting interrupts on behalf of the device for the VM. And with IRQ bypass, just as the name implies, we can actually finally take a hypervisor out. So we're bypassing the hypervisor. The nice thing about RISC-V is that it's already tried to consider IRQ bypass in its specifications. So when you actually inject an MSI into a virtual CPU, it can have a virtual IMSIC. So this is from the AIA spec, which was recently ratified, actually. This the IMSIC support. And so when you want to inject into a virtual IMSIC, this is actually possible by just writing to a guest interrupt file. It can have its own address. So these VS file things that I have depicted there on each actual IMSIC, these are the host level, the hardware IMSICs. These are these special address ranges which are going to be used, dedicated to a guest, to a vCPU, which will be able to take these direct writes and no hypervisor needed in order to inject the MSI. I've also got some showing there, like when you migrate the vCPU, you're going to actually have to change your VS file. So even if you have a dedicated VS file, you only have it as long as you stay on one CPU, right? So move, you change. And then there's also another concept that we have with the IMSIC support for virtual CPUs, and that's this IMRIF thing. So if you don't actually have one of these special guest files available for your vCPU, maybe you've only got, actually you will only have a set number, and you want to swap them between mini vCPUs. So you'll actually be swapping out this guest interrupt file actually to a memory resident file, or backing again, or maybe actually you don't have any at all guest interrupt files. You'll be using these IMRIFs. So this is just an in-memory representation, a place where you can write into a bitmap actually for pending interrupts instead of directly injecting the MSI. And then the hypervisor will see these writes to these IMRIF files and inject interrupts to the guest. Now, the IOMMU, which was also V1 spec, was actually also ratified this year, also knows how to handle IMRIFs. So for being able to just write to a guest interrupt file, nothing special for an IOMMU, right? You have your IOVA, mapping directly to the MSI guest file, and you can write MSIs directly there by just translating. But with the IMRIF, it needs to be aware that the address is going to be writing into an IMRIF, because now you're not just putting the MSI in the MSI file, but you're writing the bitmap. And then after you've done that, after you set that pending bit, the IOMMU will actually inject another, it'll trigger an interrupt to give a notice to the hypervisor. So, hey, we actually wrote this thing into your IMRIF, but, of course, it's not going to get delivered to the guest until after you do something about it. So that's the notice MSI. All right, so that was the introduction. So IOMMU supports being able to inject MSIs into IMRIFs and also, of course, into guest interrupt files. It has its own MSI table for that, for the mappings. And the IMSIC knows how to support these guest interrupt files in these IMRIFs. So we can actually have this full connection between the remapping in the IOMMU and delivery of the MSI to the vCPU. But we have, so these two entities we have the vCPU controller, KVM, the hypervisor, and we have the IOMMU, the remapping. So these two entities need to somehow communicate, and of course, we don't want to merge these two subsystems together with hackery and violate abstractions. So the question is how to do that? Well, VFIO already provides us quite a nice framework, or as Alex said, it's already plumbed. And so as far as getting IRQ bypass configured and set up, and being able to start doing this mapping for DMA, particularly, also, VFIO does that for us. And so KVM already has that framework in place too. We just have to turn it on for RISC-V, which is pretty easy to do. And then once we have this routing function implemented, we can start trying to configure our bypass. And so kind of the bridge between these two components, these two subsystems, KVM and the IOMMU driver, is best suited by something that speaks IRQ, which would be an IRQ domain. And with an IRQ chip dedicated to an IRQ domain that the IOMMU instantiates, we can implement IRQ set vCPU affinity, which is a function that's provided as well. And we just need to implement that for this particular IOMMU design. So like I said, the guest interrupt file is actually pretty easy. If you pass in, the GPA and the HPA for the HPA of the actual guest interrupt file, GPA that the guest wants to use, that it believes that its S mode interrupt file is sitting at, then you just go ahead and allow that mapping in the IOMMU and things work. And then the IMRIF stuff is where things get more complicated. So that structure or pair of structures I have on the top of the screen there, I've been iterating on that for a while, trying to decide, this is a protocol that we have to define to be able to communicate the information we need from KVM into the IOMMU. And I'm not really satisfied with it yet. It doesn't matter too much. We can iterate on that even after we get to some step, because it's it's an internal kernel thing. It's not like we're going to advertise it externally. But whatever. The thing I'm probably least happy with is the bottom arrow. So right now, the way I have it set up in the POC is that when you need to use an IMRIF, so the hypervisor is telling the IOMMU driver we're going to use an IMRIF, passes in the information it needs, which is described in that structure there above. And then it's just getting this IMRIF data structure is just getting tapped onto a linked list, which was going to get iterated every time a notification MSI gets sent, which will be actually handled directly by the IOMMU itself. And the reason I have it that way is because this division between what goes in what side, the left IOMMU side or the right KVM side, is kind of hard with regard to this particular MSI notification thing, because the MSI is being triggered by the IOMMU. So, it owns this. It knows it can easily set up a handler for it. But the actual action that should be taken is one done by KVM. So currently these callbacks get called from the IOMMU driver telling KVM to go do stuff. And that's already a bit ugly and a bit of a violation of abstraction, I think. You do it KVM to register the handler for the interrupts that will be generated by the IOMMU, but KVM doesn't know the virtual interrupt numbers that it will need to register these handlers for. So I don't have this actually figured out yet how we're going to do that, and that's one of the reasons I'm here, to ask you guys for advice. And maybe one of you have the answer, and I'll just write it down and go home and do it. So, anyway, I'll just open it up for people who want to start commenting or suggesting stuff. No answers. Okay. Yeah, go figure it out. Okay. Anyway, so if there's any, so the other reason I want the KVM to actually handle this is because of being able to deliver, being able to define where that MSI notification handler should be. So I actually think it should probably be under KVM. KVM will be able to set it to the same physical CPU as the vCPU that this MREF is dedicated to. This would have the nice effect that you're not interrupting something else for a vCPU for work being done on the behalf of some vCPU. And it would actually even probably, or very likely, if that vCPU is running, it's going to actually create an exit cycle, and then it's going to get to the interrupt delivered even sooner. So that's another thought. But anyway, so talk. Just throw that randomly into the room and see who catches it.
Yeah, or maybe we've all been shouting for 3 or 4 hours or whatever it's been.
Yeah,
I'm
it's
about to fall
lunchtime.
asleep,
I got the perfect timing when everyone's hungry and already brain dead. Just thinking about what they're going to eat.
The RISC-V have the AIA have a lot of fails, VS fails, and for different vCPU, and my question is, the IOMMU is just to remapping the vCPU fails to the address space. That means if one vCPU schedule out, so if somebody want to, if some device throw the IOMMU to raise up to set the IRQ, VIRQ, it would raise up a page fault or access fault or maybe some special trap.
So it depends on, so I mean, all of the mappings in the IOMMU are going to be device specific, right? They're part of that device context only. So you won't have any sort of like mapping where you're going to go off into nowhere, because you just actually won't go there at all.
Yeah.
If none of the vCPUs that are currently scheduled are going to be using that. So if you have multiple vCPUs for one VM where that device has been assigned, then they should all end up with the same mappings eventually, right? So because when you launch the guest, then you set these affinity. So if you need to move the IRQ, if you need to migrate because you've actually decided that this vCPU is not going to run and that one will, then that's when, go ahead.
Asking about the case where a vCPU doesn't have a guest interrupt file allocated to it because like you have more vCPUs or it's scheduled out or something like that. That's what the memory resident interrupt files are for. So it can just write the pending interrupt to memory, and then the IOMMU just notifies the hypervisor that it needs to go schedule out that vCPU. I think, is that the scenario you're talking about?
I mean, actually, when the devices write that field, that VS field, and it's called raise up different kind of fault, page fault. If the page fault, we just think about a normal IOMMU write page fault, but for the IRQ scenario, maybe we can use another trap to determine this specific usage. That will maybe that means if we reuse the right page fault, that would go into a complex path, and you need to determine that. And if we give a specific one, maybe would improve the pace of the IRQ
of the remap
trap.
The IRQ.
Another thing I mentioned this question is I want to compare the such as the ARM previous implementation. They just use the vCPU interface, and they didn't use our AIA so many VS fail mapping, because that's serious. And for the hardware, it's a little bit bring some PTW into the interrupt, into the AIA, into the interrupt stuffs. Actually, in ARM have a simple implementation. That's the vCPU interface. So, but the advantage of the AIA is it could decrease some context switch, because the mapping is there. So if you want to change the mapping, you just change it, such as SATP root page, similar like the page table. So these two kind of mechanisms, how do you compare them? I mean, the traditional vCPU interface or AIA, this page walk based IRQ mechanism. Yeah.
So so I don't think I completely understand the question on what I'm trying to compare, but I think, so you want to know about the difference between knowing that you've hit this MSI page fault versus a normal DMA, or versus a different type of MSI, or?
Yeah, I think for this AIA implementation, we have a simple one. Previous such as ARM vCPU interface, that's simple. Okay.
What do you mean by simple? Like, we are talking about the AI spec which has the VS file. So if the vCPU schedule any writes to the VS file, directly gets, and then vCPU gets the interrupt. If vCPU is not scheduled, either mref or the software file gets kicked in, and then the interrupt bits will be stored there. And then whenever the next vCPU gets trying to like vCPU load, you check whether the pending interrupt bit, and then it will schedule that. But I don't understand what do you mean by simple interface. Like ARM have
vCPU interface that didn't like his hardware is like ours. He just put a vCPU interface, and no many you need to prepare the many files, mapping files, VS files. There's no in their design, and the disadvantage of that design is you must switch context more than the AI.
The memory mapped interrupt file, the memory resident interrupt files already provide the interface to do that on AI. So like you could theoretically just have one guest interrupt file, and in software switch back and forth between a bunch of memory resident interrupt files. Yeah, so the IMRIF interface allows you to do the same thing on RISC-V that you would be doing on the manual context switching in software that you would be doing on ARM. So it's all the functionality to determine that this is an MSI write and do special things with it is already implemented in the RISC-V IOMMU spec.
It's a special table for MSIs with special PTE format, so it knows when you're doing an MSI translation. But anyway, I'll talk to you later.
You got one question in
to
the
make
chat
sure I understand.
from Jacob Pan. He wants to know if the IOMMU stores the host physical address of the MRIF.
And it stores the host physical address of the
MRIF.
Yeah, it does. Yeah.
Okay,
Yeah,
thanks.
Yeah. It's specified, so it knows exactly where it's going to write to that bitmap.
Yeah, we have 18 seconds. So speaker gets, if you gave the speaker, you can take one if you want. Yeah.
you.